Yes, we're staying for another week.
Oh, yes. Yes, wants to say more talks. Come on. Okay. Folks, one quick announcement. Come on, Ali. Come on, guys. Remember to take down your posters between or close to noon-ish during the lunch break. They're going to take down the stands at 3 o'clock or something like this. So do that during the lunch break, please. If you want your posters to be recycled, if you want your posters to stay here at the University of Texas, please let me know. We can always carry them to the department and display that for a little bit longer. That's an option, right? Beautiful posters, man. Okay, let's get started. The new session, binaries.
Well, the first speaker of the day is Valeria Carroll. She's going to talk about constraining the Milky Way's potential with double white dwarfs.
Now I have to go to the trouble. Yeah, I can put. Okay. It's not gonna work there. We have a badge. Yeah. Yeah. Don't roll. Oh, we did it. Enter here. Forwards. Okay, so I'm Valeria. I'm from Leiden University, and with the so far we studied the Milky Way through electromagnetic light only. And with the project that I'm going to show you, I want to introduce the idea that one day we will be able to map the galaxy using gravitational waves from double white dwarfs, as it has been done with the electromagnetic tracers. Does it work?
Oh, yeah. That's why it's not working.
Okay, so Milky Way is really the only galaxy that we can study in detail because we are living in it. But because we are inside the galaxy, it is difficult to see its large-scale structure. So historically, astronomers addressed this problem by defining some discrete parameters of the galaxy, like the bulge, the disk, and the halo, and by defining their structural parameters, like their masses, their radii. And by measuring these parameters, we can compare our Milky Way to other observed galaxies and compare it with the cosmological simulations to test our galaxy formation theories and the Lambda CDM model. But it's not always easy to measure these parameters, and this is because of the dust extinction, because of several biases, and because the distance is difficult to measure at all wavelengths. And here I'm showing you just one example for the measurement of the disk scale radius on the x-axis and for the disk scale height on the y-axis. And all colored markers are different electromagnetic tracers. So you can see that there is a lot of spread in both directions, and there is no consensus yet on the measurement. But we can overcome these difficulties by observing through gravitational waves where we don't have dust extinction. We can model our biases, and distance can be measured directly from gravitational wave observables. And in particular, LISA can be a game changer for the Milky Way studies. And LISA stands for Laser Interferometer Space Antenna. It is an ESA mission that was approved last year, so it's going to fly. It will consist of 3 identical spacecrafts connected by laser links in equilateral triangle configuration. And the most impressive thing of LISA, that is the arm length of the LISA triangle, will be of 2.5 million kilometers. That is almost 3.5 times the radius of the sun, or if you prefer, several hundred of white dwarf radii. So this will be really, really huge detector. And if we want to understand what LISA is going to see, we need to simulate the galaxy. And to do that, I took a binary population synthesis code from Sylvia Tunen that currently contain only essential component, the bulge, the disk, and dark matter halo. We populate this potential with the population synthesis code using time and space dependent star formation rate. So you can see here that my galaxy is growing in time. And the next step, we simulate the gravitational wave signal from these binaries. So I will show you directly the result. So this is the Milky Way as it will be seen by LISA through gravitational wave radiation from detached double white dwarfs, and you can clearly see the bulge and the disk. And just to give you a few numbers, here I'm showing you more than 26,000 binaries that LISA will resolve and measure parameters individually. And the typical error box of the LISA mission on the sky for these sources will be of around 1 square degree. And for almost 8,000, we will be able to measure distance up to 30%. And curiously, almost for 100 binaries, we will have distances measured better than 1%. That is very impressive for astronomy. And the most curious thing that these binaries will not be the close by, this will be really spread around the galaxy. So now we can step back and look at the Milky Way from the external point of view. So here you see the side and the top view of the Milky Way, and the sun now is here. And you can appreciate that LISA will be able to cover the whole surface of the disk, including also the opposite side of the galaxy. So we can take now these maps and study the density distributions of the LISA detections. So let's look at the bulge first. And here I'm showing you the number density distribution versus spherical radius from the galactic center. And this density was worked out just by binning LISA detections in spherical shells and divided by shell volume. So the magenta points are my simulated data. The black solid line is their underlying model, and you see its analytical expression here. And the blue line with the blue band is the best fit with 3 sigma contours. So you can see that the data nicely follow the model. And I want to highlight that we can fit the disk, the bulge scale radius with the percentage precision. And likewise, we can do for the disk. So here I'm showing you the disk radial density profile and vertical density profile. And I build these profiles just by, again, binning, in this case, in cylinders, and in this case, in vertical layers. And again, you see that we can fit extremely well the disk scale radius and the disk scale height. And this is a competitive measurement with our current electromagnetic tracers. So far, I left out this normalization factor, but I want to derive it now. And I will use electromagnetic counterparts to do that. So a good way of finding short period binaries is to look for eclipsing sources in wide optical surveys. I choose Gaia and LSST. So for each binary in my galaxy, I compute how likely it's to be detected by one of the 2 surveys given the cadence of Gaia or LSST observations. And I found 80 EM counterparts in total. You see them in blue. And what I want to use is their proper motions and parallaxes. And what I found that for all 80 binaries, we will have precise proper motions, but only for a quarter, we will have good parallaxes. So my idea was to combine parallaxes with gravitational wave distance measurements using parallaxes as priors, and this would give us an information where these binaries are located in the galaxy. And on the other hand, I can use proper motions to derive their rotation speed in the Milky Way. So I can build a rotation curve with gravitational wave sources. And you see again in black, these are my simulated measurements. The black solid line is the underlying total rotation curve, and the colored line are the contribution from different galactic components. And again, I can fit the data with the model. And this time I did it by fixing those parameters that I found before, and by leaving free the remaining 4 parameters of my Milky Way potential, that are the halo density, dark matter halo density, dark matter halo scale radius, the disk stellar mass, and the bulge mass. And here you see the posterior probability distributions for these 4 parameters, where the blue lines are the true values. So if you look here, you can see that we can recover extremely well the mass of the bulge. We can also recover the mass of the disk with some larger errors, but this is because the disk and the halo are degenerate. And indeed, we cannot constrain the halo parameters, but this is because we don't have EM counterparts far out in the disk, where in the galaxy where halo contribution starts to dominate. So for a different potential, the result would be different. And so to conclude, I would like to say that this is, of course, was only a first step towards understanding how we can study our galaxy using gravitational waves. And I showed that LISA can be used as a tool to do that. I also showed that galactic double-wide dwarfs can provide precise, unbiased constraint on the scale length parameters of the Milky Way. And when we combine their observations with the electromagnetic observations, we can also constrain the masses of the baryonic components of the Milky Way. So my take-home message for you is that with the double-wide dwarfs, we will go from multi-wavelength to multi-messenger study of the galaxy.
So we're going to go through the questions for Valerie.
So when you were showing the constraints, it looked like your kind of ability to constrain things in the bulge was really dependent on the fact that you had one system that wasn't kind of in the solar neighborhood.
Yeah.
Can you comment on the possibility of how many you actually expect to find, near the galactic, under 12 parsecs or 2?
Yeah, so the one system that I have there actually has really high chance to be detected because it's right, at a high galactic latitude. So in my simulation, it's actually very likely to be detected. And perhaps we can have a few more systems there, but of course, the majority will be in the solar neighborhood.
Excellent work. Is there a reason you excluded interacting?
Yeah, so there is a reason, and the reason is because I didn't mention it, but it was an important point. I'm using here only those binaries with precise distances, and with interacting binaries in their gravitational wave signals, there is also a component of accretion and tides, and we cannot disentangle that without knowing more from EM point of view. So this is.
Any more questions?
Why do you have that cross-like structure instead?
Yeah, sorry, this is because the axis ratio is not equal. So, yeah, sorry.
Any more questions? Okay.
I'm not sure if this is a silly question, but with the gravitational wave detector, does it detect all of these sources at the same time? So you have a
yeah, so actually these are double white dwarfs are extremely boring gravitational wave sources because they're just monochromatic. But the real challenge for the LISA mission will be to disentangle all these thousands of binaries that LISA will see simultaneously in the data. So this will be like a real data analysis challenge to do.
We don't have any more questions. Let's thank Larry. I got experience in it. You can put it here. Come in here. If it, oh, it's. And this one. The pointer is this.
Okay.
Or, oh, I need just a minute. So now the talk is from Jody Iser, and it's about white dwarf collisions and the meteoritic neon E anomaly.
Okay, thank you. What I want to present you is a very speculative idea to try to about a possible scenario that could explain the anomaly of the neon E that was found 50 years ago in the meteorites. Usually, it has been thought that the collisions, the frontal collisions between white dwarfs and white dwarfs, they are rare events, and that they only can occur in dense core of the globular clusters. So, for this reason, it was neglected as a nucleosynthesis agents. However, the perception has changed recently by including the hierarchical triple stars. In fact, we know that the isolated, the majority of stars, they are forming multiple systems, and in particular, there are these triple systems which consist on a binary and a third star in such a way that this binary behaves as a binary and is perturbed by this star. So depending on the eccentricity and inclination of the orbit of the third stars, then these two stars, they experience cycles where they can approach, and they can approach to the point that at a given moment they can collide. And this scenario has been proposed as a possible scenario for type 1 supernova. Nevertheless, to my knowledge, at present, we have not true evolution of the triple systems, in the sense that to follow the evolution of this binary within this system. This scenario has been, it seems important, and in fact, Katz and Dong, they propose it could be enough to produce, to account all the type 1a supernovae. I don't believe that, but perhaps this scenario can account a substantial fraction of type 1 supernovae. We can use the image that was proposed by Timmins, which we have moved from a duel with a single shot pistol to a duel with a machine gun. So the probability to obtain collisions is much higher with these systems. The problem that is interesting me is not the shot that produced the explosion, but the other shots. Because these other shots, these collisions, they can induce partial nucleosynthesis in the star. They can eject matter. And so what we are going to inject in the interstellar medium is something that is completely different of what is usually obtained from the normal nucleosynthesis with supernovae, with AGB star, and so on. In fact, we studied such collisions, and we saw that effectively the result strongly depends on the geometry, the mass, and the chemical composition of the stars. And so we have a large variety of scenarios. The chemical composition of the white dwarfs, which can be ejected to the interstellar medium, is a core made of oxygen. Then we have carbon that grows, as it was shown by Jean Michele, And then we have here neon 22 that is which has an abundance that is equal to the initial abundance of carbon, nitrogen, and oxygen, and we have here S elements that were produced during the AGV phase. That composition changes with time, and there are two mechanisms for changing that. One is the gravitational settling of the neutron-rich species to the center, and the other is the settling, the stratification induced by the freezing of the star. If we consider the freezing, and for instance, you adopt the Segre-10 phase diagram for the ternary carbon-oxygen-neon, what we see is that carbon and oxygen, they behave like a spindle form in the center, and so when they freeze, we form a solid that is rich in oxygen, and carbon floats and mixes outwards. The result is that the total amount of oxygen in the center increases and that of carbon decreases, and this carbon translates to here. But when the abundance of carbon is larger than 75%, then carbon and neon form an azeotrope. They mix well together, they cannot be separated, and that expel the oxygen. And the result is that we form a layer here, a very thin layer that is made only by carbon and neon 22, completely mixed. So what can happen? Well, imagine that we have a collision. This is a simulation that we have done in which we consider two stars of 0.64, 64, and then the parameter of collision is just the radius of the star, so this is the density. So we see that they collide, the temperature increases, there is some nucleosynthesis here. But what is interesting is that after the process, this layer made of carbon and neon 22 can survive. And if it can survive, it means that it will be expelled to the space. Probably it will condense. It can survive the interstellar shocks, and it can be incorporated to the nebular material, in particular to the primitive solar nebula. So if you go to the Stardust market, that is the primitive solar nebula, we see that there are several grains of dust. That we have found nanodiamonds, silicon carbon, graphites, oxides, and many more. So here, I recall your attention to the graphite. The graphite is important because, for two reasons. The first one is that graphite can only form if oxygen is completely absent, or if you prefer, if there is more carbon than oxygen, in order to have free carbon to form this graphite. The second property that is also important is that also in this market, you take, for instance, the grains of graphite that was obtained from the Murchison meteorite, that is famous because it contains organic and prebiotic material, and then you see that within these graphite grains, there are those that they are called light, and then we have two kinds of grains, one with the structure of an onion and another with the structure of a cauliflower. The onions are a local product, it's a product of the solar system, but the cauliflower, that is made of other grains, it comes from the interstellar medium. It represents pre-solar material. And these cauliflowers, they are characterized because they have an excess of neon 22. And even there is 8 grains that have been analyzed, even there is one where the abundance of neon 20/22 is smaller than 0.01. And remember that the solar value is 13. So the question is, are these grains produced by the collision, by matter that was of the galaxy? Here we have the moment where the solar system formed, of the order of 9 gigayears. So here we have just a time at maximum of 9 gigayears to produce such grains. And here, this is the lifetime in the main sequence. I have not taken into account the change due to the difference of metallicity. And then I have added the time that non-DA white dwarf that cools more quickly takes. And as you can see, if the mass of the progenitor is larger than of the order of 3, we have time enough to produce such grains. Well, in fact, here I have assumed that it's all the white dwarf crystallizes, but this excess of carbon can be produced in the inner layers, and so we can reduce such age. This is just an overestimation, probably. On the contrary, if we consider DAs, we see that they have had no time. So this is something that has to be analyzed with care. To conclude, because it's finishing my time, remember that, well, we believe that this is a promising scenario that can account the chemical anomalies that we observe in meteorites. However, there are plenty of questions that we have to solve. First, to explore the enormous amount of parameters that we have. Then we have also to study what happens with the isotopes in the interior of the white dwarf, because those which have an excess of neutrons is going to settle by gravitational diffusion. And then also we have to know what happens with the multi-component crystals. This is a problem that we have in common with people that they are studying the outer layers of accreted neutron stars, of the X-rays sources. Also, we have to see what is the dynamics of the formation of this dust, because these conditions that are not exactly the same as an AGV or supernova, which is the complete nucleosynthesis, and then also to see if the collision rate is high enough to produce such anomalies, or vice versa, if such anomalies can introduce constraints to the number of collisions that we can obtain. So this is a completely open problem. Thanks. Just to finish, I cannot resist concerning the problem of the times that we have to freeze the star, that we have had recently the visit of the Oumuamua, that it was an extrasolar asteroid, that is the first one that we have detected, and it seems that the frequency obtained exactly from one event is of the order of 1 per year within the 1 astronomical unit. And now there are already people that is proposing missions to go to the asteroid and to take samples. Of course, since they are extrasolar, we have obtain and analyze the samples of the interior of white dwarfs. And this is a tool that we can add to the asteroseismology techniques, and we can add also to the characteristics of the magnetic field. That's all. Thank you.
We're about 2 questions to it. There and then here. Oh, here. That's.
Hey, Jordi, about the collision rate, I just want to say that we have a paper on that last year where we calculated the evolution of stuff.
Sorry, I have problems with my hearing.
About the collision rates of white dwarfs from triples, we have a paper on it from last year where we calculated the evolution of triples, combining stellar evolution and three-body dynamics from the main sequence onto to the collision. And what we find is that the rates are very, very low. So they're 3 or 4 orders of magnitudes below the type 1A rates.
Well, so this means that you cannot produce, well, the contribution to type 1 supernovas are small, but anyway, the shots that can inject material from the white dwarf to the interstellar medium is still possible.
Yeah, exactly. But I was just wondering if you take a rate of say 10 to the minus 7 per year in Milky Way, would that give you enough? Because that's roughly what we're doing.
It's possible, yeah.
Could you remind me roughly what the oxygen 16 to 18 abundance was in the?
Sorry, the reverberation. I apologize.
So I was wondering about the oxygen 16 to 18 abundance in that grain, and whether you could also explain that with this picture.
Yeah, this is one of the problems that we are looking how to solve, because in this first calculation within an ad hoc chemical composition, we have not computed the oxygen 18, or we produce very small oxygen 18. This is true, but we have to improve the initial models.
Any more questions?
Very nice. Can you tell us, was there any nickel 56 produced in this great collision? Was there, would it be visible as a chance?
Sorry, I apologize.
Was there any nickel 56 produced? Would this be visible in this grazing incident collision?
In principle, the production in these models, the production of nickel 56 is not very high. At maximum, we could explain a dim type 1a supernova, but nothing else. Probably it could be visible, and especially if this occurs near enough, it could be detected with gamma rays with the future gamma ray detectors in space.
So let's take Jordi again.
Okay.
Yeah, there we go. This much. Our next speaker is Tom March to talk about the spin down in the White Dwarf Pulsar AR Scorpius. Yes. Where's the pointer?
Yeah, so what's the instructions here?
Here, this pointer?
Yeah.
Forward, back.
Okay. Right. Okay, so I thought I'd start out with I was going to thank Jay for his heartfelt comments earlier on for us Friday Wooden Spooners. And he is also, I was going to apologize to him because of he was talking about trying to extend to the wider community. And the object I'm talking about here is of no interest to cosmologists and no interest to planet people either. So I'm going to withdraw the apology, though, since Jay told me he had an urgent appointment last night with a whiskey distillery in Waco today. So that's the end of my apology on that one. Okay, so let's get on to the science. So this is a very unique object, so the White Dwarf Pulsar, which I presented a couple of years ago in Warwick. And I just want to update you on a very important aspect of it, which is the spin down of its white dwarf. So the outline, I'm just going to introduce a little bit just to remind people, or some people might not know about this at all. And then the main thing is the white dwarf spinning down, because it's very crucial to the model of this particular system. And I'm going to look at how we actually get this object. It's extremely difficult to understand how we actually get it in its current configuration. And finally, I'll just, if I have time, I'll just talk a little bit about some new data, trying to sort of see whether we can use this as a timing source. So it's sometimes called the White Dwarf Pulsar. It has this amazing light curve here. This is the optical light curve of AR-SCO. The main thing to point out here is going from zero here, the zero flux, the linear scale here, and every one of these is real. These are very large pulsations which are happening every 2 minutes from the spinning white dwarf. And even this thing up here is real. So this goes off the scale here. So sometimes it can brighten by more than 6 times in 30 seconds. So it's a very variable object on those short time scales, but actually on a longer time scale, it's fairly consistent. You're also seeing here an orbital period as I talk about. So the fundamental period here is from here to here. That's 2 minutes. There's an interpulse as well. So you're seeing a rotating dipole, we think. It's also incredibly unusual in being a very strong synchrotron source. So here you show these are the components of what I'll talk about being a binary. This is the maximum white dwarf. We don't actually see the white dwarf directly. And it's got a companion M dwarf, but it's actually dominated by synchrotron emission from the M dwarf induced by the white dwarf. Extremely unusual. There's only one other object which is really like that. Sorry, I'm not very good with this thing. Sorry about that. Okay, and then finally, as I say, it's a binary. You can see the M dwarf at the sort of fainter part of the cycle, fainter part of the orbital cycle. The M dwarf is nicely visible, and you can see it orbiting. So we know pretty well the orbital period is well defined. That also allows us to get some dynamical constraints, which are quite important in this particular system. Okay, so just to summarize, these are the sort of key facts about ALSCO that you should know. I don't know if anyone's aware of this sort of series of bluff your way in second law of thermodynamics or whatever. There's a whole series of these things. So if you had to do that in ALSCO, these are the things to know. Magnetic white dwarf spinning on a 2-minute period in a close binary of 3.5 hours with the M dwarf companion. 2-minute pulsations seen at all frequencies, radio, X-rays, optical, infrared. It's unique in having these radio pulsations amongst white dwarfs. Kinematics suggest white dwarf mass around 0.8 solar masses and the M dwarf around 0.3 solar masses. This is my one little shout out to Gaia. So Stefan, if you're ready, or maybe he's not here. So I estimated from the M dwarf 116 parsecs and 118. So that was a bit of a success. But Gaia's improved the error bar. ALSCO does not accrete. We think it's spin powered, but that's the main topic of this talk. Okay, so in the discovery paper, when we discovered it, we didn't have a lot of long-term data, but it does actually appear in the Catalina Sky Survey. And we were able, well, I thought I was able to measure a spin-down rate from those data. I'll be talking about exactly what those data consists of. So this shows a plot of the frequency derivative versus the frequency deduced from these Catalina Sky Survey data, small telescope data taken over a few years. If there's no frequency derivative beyond this dashed line, negative meaning a lower frequency. And this is the value I measured. Don't take too much attention to the exact values here, but the important point was that implied a really quite large spin-down luminosity. Okay, so a substantial fraction of a solar luminosity just in the spin-down power alone. So we put an upper limit around 10,000 K on a white dwarf. It may be fainter than that, but that means the spin-down luminosity completely outpowers the electromagnetic luminosity of the white dwarf itself. And it's actually something like 15 times more spin-down luminosity than we actually see in the synchrotron. So there's more than enough. That's why we think this is a spin-powered source. And there's also no direct evidence for accretion. However, a more recent paper that came out earlier this year cast some doubt on that. This is by Steve Potter and Dave Buckley. And they did much more intensive photometry since the discovery, high-speed photometry, actually multiple points in long time series over 3 years, and found no significant spin derivative. In fact, in an earlier version they sent me, they'd actually saying that they were setting an upper limit quite a lot lower than the value I measured. But they eventually just essentially came out saying they can't find a spin derivative, and they suggest that the CRTS data are too sparse to actually measure the spin derivative. Given its importance for the system as well, this is an important thing to say. They're basically saying I'm wrong, okay, that's fine. Okay, so that's sort of fighting talk. What do they mean that this CRTS data are too sparse? I just talked about it, but well, it's not that sparse. But here's the densest part of it: 2 days, 8 points. Yeah, well, maybe an average of 1 every 13,000 minutes, and I'm trying to constrain a 2-minute thing. So you may think they've got a point. Okay, you may just be thinking that. Okay, but let's see. So we got some more data. I've been taking data since the discovery. So this is the very first data we got, 2015, 16, 17, 18. This is about 60 hours of data here. That's not all the data we got. These are quite long time series, some of these. This is just an attempt to measure the pulse time. So it looks pretty ratty here. Maybe you can see some effect, but it's not very obvious. However, there are strong systematics in there, and we can improve it quite considerably, as you'll see. So first of all, just zooming around the little bit around here, there's a stretch of data here where you can sort of see there are some systematics here. There's about 2 orbital cycles here, and there are strong systematics on the orbital cycle. And so we can use those to try to improve the pulse times. So just folding it on the orbital cycle, you can see there's a lot of consistent behavior there. And I can use that, I can develop a Fourier model to then try to remove that. And doing so, and along with some extra sort of secular terms, we end up with the timing residuals like this. And this is a scale from -5 to +5 seconds. So we really can get some pretty decent times. And there are phases, particular orbital phases, when the pulse times are really quite tightly defined. There's a scatter of only 1 or 2 seconds there. And so this is really enough to actually get us the pulsation ephemeris. So if I just extract those particular times, and here we are, there's absolutely no doubt whatsoever this thing is spinning down. So this is an O minus C, observed minus calculated, seconds here, where is it, 2 to 2.5 around here. The pulses are getting later, the thing is spinning down, and so there's no doubt about it. The one thing that's changed is about spinning down about twice the rate I actually measured before. So the CRTS weren't perfect for sure, but there's no doubt it's spinning down. It's spinning down, the spin down luminosity is around 3/4 of a solar luminosity. And then, slightly unluckily, between my abstract and this meeting, a lot of my thunder was taken with this result here from Stiller et al. Well, basically, they get exactly the same value as I do. It's consistent to 1.5 sigma, so there's very little doubt. Just briefly, just to revisit the CRTS data. This is a sort of phase dispersion diagram of the quadratic term of the ephemeris versus the period. If there was no change at all, it would have been here, the actual minimum value around here, and this is my predicted value. So this tends to show that the CRTS data are not only more or less consistent with what I've measured, but it's been spinning down at the same rate in all the time. This goes back to around 2007 that we've been observing this thing, so it's not too surprising. Okay, so I'm going to move on to the problem with actually making AR scope, which is really quite major. It's a very interesting problem, this. So we've got this thing spinning at 2 minutes, okay, and we think it's a magnetic white dwarf. To actually spin something up, it's got to be spun up through accretion. White dwarfs aren't born at 2-minute periods, so assuming at some point it's accreted, you have to be able to overcome the magnetic pressure through the accreted material to actually, and right down to the co-rotation radius, where the Keplerian orbit matches the spin period. And that gives you a sort of fairly simple relation. There's some fudge factors, of course, but you're going to see that the problem here is no small fudge factor is going to address it. So this is the ram pressure on the left versus the magnetic pressure on the right. This is the magnetic moment of the white dwarf. Katz then estimated the magnetic moment just from the observed torque on the white dwarf through this equation here. And you can solve these two to actually deduce what is the accretion rate necessary to have spun this thing up. Thank you. Okay, and it's horrendous. Okay, 10 to the minus 2 solar masses per year. No way an M dwarf is going to supply that. Okay, so I should also say that this will there's a very large field here. It could be maybe somewhat smaller than that, but it's certainly going to be in the hundreds of megagauss range in this system. The solution, I think the field must have been much lower in the past. I don't think there's any other way around this. It must have been much lower. A couple of different ways. It might have once been buried. There are some suggestions that you can actually bury the accretion when the thing is not spinning very fast, but bury the field. Or maybe it just spontaneously emerged. So I'd be very interested if any of the astroseismologists ever come up with some evidence for buried magnetic fields inside white dwarfs. This is a big field, okay? I'm sure you couldn't miss it, but it may just be, of course, the thing doesn't pulsate, so unfortunately. Okay. The emergence timescale, either way, whether you, whichever of those two models might be right, has to be moderately short. So just very some simple models trying to match the current frequency and the current frequency derivative, I think the field's got to emerge on a timescale of around 50 million years. That compares with theoretical estimates, which must be fairly uncertain, of 300 million years. So it's not too far out, I'd say, but certainly got to be reasonably fast to actually match the system. Okay, finally, a completely different thing. So moving on from here, is AR-SCO a good timing source? So here I show some simultaneous 5-band photometry taken on a 10.6 meter at 10 hertz. That's really a bit over the top maybe, but we're just trying to see how fast things go in this thing and how well you can time it. So if I just expand a little bit, this is quite nice data. It's 10 hertz in the top 4 bands, a little bit slower in the U band. So this is U, G, R, I, Z. Okay, and this is just one pulse. And what I hope you can see there is that there are actually some color differences. They're small, but then they're not insignificant. So if we look at the U band here compared to the Z band, and you can sort of see there's features here. So that's going to affect the timing. And so just to show you that, so the little sort of rainbows, I apologize for the colorblind in the audience. What I'm showing here are the pulse times, just individual pulses in each of those colors here. Okay, so you can see it along here. This is sort of quite consistent here, and it's blowing up here. And so just look at the little rainbows here. So UGRIZ there, UGRIZ. You can see it having the same pattern. Sometimes they spread out, and sometimes they're quite consistent. So it's showing some behavior there, but it's also meaning that as a timing source, it's somewhat compromised. Rather interestingly, it seems to reverse the pattern. So you've got UGRIZ that way, and it goes UGRIZ that way at a different orbital phase. So that's only early stuff, and I don't understand that. Okay, I'll leave you with the conclusions. Thank you very much.
No questions?
So when you show the light curves, what is the amplitude? What is the axis? Is that magnitude plus?
They were linear plots. So I mean, the very peak it gets to is around 12.8 in magnitude, and the faintest it gets is around 17. It's a very variable object. This is not 10%.
So, Tom, you mentioned that the origin scenario is a bit of a mystery because the Dwarf can't possibly have provided that much mass over time to spin it up. Can you rule out a tertiary scenario or something?
I haven't thought about it, so I don't think I can off the cuff. So if you can think of a good one.
Any more questions? Oh, if you don't have any more questions, let's think, Tom.
Yeah.
This thing shouldn't roll here.
Yeah.
So the next speaker is Parsons. Stephen Parsons talking about high precision studies of white dwarfs and eclipsing binaries. That's for you too. It's for you. Can you put
Okay, good morning, everyone. So yes, let's get straight into it. Yeah. Okay. Right. Okay. So I hope that I don't really have to convince too many of you of the importance of the mass-radius relation for white dwarf studies. It essentially underpins virtually everything that we do with white dwarfs. And so therefore, it's quite important to test it and test it in a very highly precise way. And as you'll see here, I've put on a few mass radius relations here for different core compositions and different temperatures. And so you'll notice that actually the radius of a white dwarf does change quite a hell of a lot for different masses, different temperatures, different surface hydrogen layers, etc., etc. So you can, if your measurements are precise enough, you can actually disentangle quite a lot of these things. And so the way we've been doing it is using white dwarfs when they're in eclipsing binaries, usually with main sequence stars, but also with another white dwarf, etc. So here, just on the right, I've shown just a sample of a few of them. You'll see there's a zoo of different systems. And these kind of objects are absolutely ideal for testing mass radius relation They're extremely abundant. There are thousands of white dwarf main sequence binaries already known, more than 100 of which are eclipsing. And to get the mass and radius is very simple. They have periods of only a few hours, so you can get your radial velocities. And so literally you're constraining the mass and radius just using Kepler's laws and simple geometry. So that you never have to do any kind of model atmosphere fits or anything like that. So they're ideal for really testing these kind of things. Since they're close binaries, they've also undergone some kind of mass exchange. And so you can have low mass white dwarfs. And these are the only kind of binaries where you can test the mass radius relation for low mass white dwarfs. Right, your wider astrometric binaries don't form low mass white dwarfs, so you cannot test the mass radius relation for helium core white dwarfs, for example, in those kind of binaries. And as a bonus, if you get the mass and radius of your white dwarf, you also get the mass and radius of your low mass M dwarf for free. There's a whole lot of issues with them at the moment, and they're increasingly important stars for the search for habitable planets. So you can, as part of Jay's push to be more important in other fields, then it helps out in that regard as well. Okay, so how do we do this? So here I've just shown a few spectra of white dwarfs here. I've subtracted off the M dwarf component, although the subtraction is never perfect in some of these systems. You see these emission lines in some of them. They're very phase dependent, so they're quite tricky to subtract. As you'll notice here, in quite a few cases, there's some metal absorption lines, so you get a lot of wind material accreted onto these systems. And actually, these lines are very narrow. They're ideal for radial velocity work. You can get radial velocities to much less than a kilometer per second precision. And so these are actually measured radial velocity curves here. So we're getting really good precision here. And so from these, you can get your mass ratios. You can measure a gravitational redshift for the white dwarf. You get your temperatures from your white dwarf fits. And then we combine that with our light curve fits. So here's a whole bunch of them. And this gives you the radius of the two objects and the inclination. And so you combine everything together and you get your masses and radii. I've swept a whole lot of stuff under the carpet there, but see the paper if you actually want to see the gory details. But anyway, so these are the kind of results we get. So the precision varies quite a lot from system to system, depending on how bright it is, the contribution from different components, et cetera, et cetera. But on average, we get a mass and radius precision of about 2.5%. In the best cases, we get to less than 0.5%. And so that's the equivalent of measuring the radius of a white dwarf at about 50 parsecs to 50 kilometers. So, I mean, that blows my mind that I can measure something that far away to that kind of precision. Good. So here on the right, I've got all of our mass radius constraints as contours. This is the 1 and 3 sigma limits. And in the background, I've plotted helium core models in green and carbon-oxygen core models in red for thick solid lines and thin dashed lines, hydrogen envelopes. And so you can see in the best cases, we are actually able to distinguish between the two different core compositions. Okay, good. So I'll plot it up like this, but I should mention actually this is a really awful way of trying to test this kind of thing. They kind of scatter all over the place. You really have to compare it to the proper model. However, it does show you the kind of parameter space we're probing here. In particular, you can see quite a lot of our measurements are in this crossover range between the carbon-oxygen and helium core models. So we can try and see if we can distinguish between the two there. So this plot here shows the ratio of the measured radius to the theoretical radius, assuming a carbon-oxygen core in black and a helium core in red. And so obviously the helium cores don't go up to these kind of masses. But you see here below half a solar mass, clearly the measured radii are far more consistent with having helium cores than carbon-oxygen cores. Now, of course, this was expected, right? I mean, this isn't kind of something groundbreaking, but it's the first observational evidence that the core of a white dwarf does indeed change when you go below half a solar mass. Okay, good. And so we can do this similar kind of exercise with the surface hydrogen layer. Now, this has a higher effect at larger temperatures. So at higher temperatures, the effect on the radius of the hydrogen layer is larger. And so you can see, for example, here in the hottest model, if you have a thick hydrogen layer here in black, you're totally consistent with the models. But if you go to a thin hydrogen layer, then you're more than 15% too large. So, clearly the measurements are favoring thick hydrogen layers here in virtually every system. Another way of showing that is in this plot here. So this shows the range of possible surface hydrogen layers for all of our objects. And so you can see essentially all of them are consistent with having a layer mass between 10 to the minus 4 and 10 to the minus 5. So pretty much thick. And actually this is showing that the binary evolution, the common envelope evolution, is actually not really having much of an effect at all on the surface hydrogen layers of these white dwarfs, which is quite nice. Okay, good. So then another thing we can do is take our spectra that we've got, and now we know the surface gravity of them. We can compare that to the surface gravity from the spectral fit. And you can see that overall there's excellent agreement. The few outliers up here are systems where the M dwarf is particularly dominant in the optical, and so they're probably not reliably subtracted off, and so there's a few residual effects there, so I wouldn't worry about these ones up here. But overall they're showing that, at least for these particular objects, the spectral fits are excellent. Okay, good. So this, although it's the largest sample ever, is actually still only probing a very small parameter range. And so what we'd really like to do is get a lot more of these eclipsing systems. We want to probe massive white dwarfs. There's nothing massive in this sample, unfortunately. You want to probe specific regions. Maybe you want to get look for eclipsing systems in the ZZ Ceti instability strip, for example. And so to do that, you need a lot more eclipsing systems. And you can't talk about the future without talking about Gaia. So here, this is some work that I've been doing recently. This is just a slice of the Gaia HR diagram, and I've cross-matched all of these sources with the Catalina Sky Survey to search for variable stars. And so this is a measure of the variability. It's very similar to if you see JJ's poster looking for the variability in the Gaia RMS, is effectively doing the same thing here. So all the black points here, the super variable ones, they're actually cataclysmic variable stars, quite a lot of which were unknown. They're not classified as cataclysmic variables. But many of the kind of pinky, purpley points are actually close binaries. So they show reflection effects, ellipsoidal modulation, etc., etc. So all the white dwarf, M dwarf stuff, they sit here between the white dwarf and main sequence. As an example here, so far I've found about 20 new eclipsing systems doing this. I still haven't done anything kind of systematic yet. That's literally just kind of looking at the interesting things. I'll show this one here. It's one we actually followed up recently with Ultracam. So this is a particularly hot white dwarf, so you can see a large reflection effect from the companion. Nice secondary eclipse when the white dwarf transits in front of the M dwarf. So this kind of system is perfect for parameter estimates. And as I said, I've got about 20 or so already. So I think this is a real nice way forward because, for example, I could say, okay, let's look in this region here. Are there any eclipsing ZZ Cetis, for example? I can look for massive ones. I can look for whatever I want. Now we're going to get just a flood of eclipsing systems. And in the future, when the actual Gaia light curves are released, it's going to do even better than this, right? Because there are a few issues with Catalina light curves searching for these kind of things. And it's, if you're trying to search for double white dwarfs, things like that, Catalina isn't ideal for that kind of thing. But in the future, it's just going to be an absolute flood. You can choose whatever kind of thing you actually want to test. Good. So with that, I think I'll finish. Thanks.
So we're gonna have one more talk for questions. It's from Howard. Yeah.
Oh God.
And we have to take this one.
So.
This one.
Okay.
So Dr. Howard is going to talk about dynamical masses of white dwarfs in nearby visual binaries.
Okay, thanks. When Barbara encouraged me to present this talk, I said, well, I don't really have that many new results since my talk a year ago in Santa Fe. But she said, well, but not everybody was at Santa Fe. So in any case, the talk is on masses of white dwarfs in nearby visual binaries, 4 visual binaries, based on mostly Hubble Space Telescope astrometry with some ground-based astrometry as well. So the 4 systems are Sirius, Procyon, 40 Eridani, and Stein 2051. 3 of these objects, by the way, in the winter sky you can see with the naked eye, Sirius, Procyon, and 40 Eridani. There are quite a few collaborators in this work, a few of whom are in this room. Sirius, Procyon, 40 Eridani, and Stein 2051, which was led by my colleague Kailash Sahu. Now, this gentleman is a famous mathematician, but it's Friedrich Bessel, who also pointed out in 1844 that the motions of Procyon and Sirius across the sky are not in straight lines, and that they must have invisible companions. Later on, the companions were actually seen by binary star observers, and both of the companions are white dwarfs. Now, one of the main motivations for our work, of course, is the mass-radius relation. And here's what this looked like in 2001. Not a very satisfactory situation. So we wanted to get much more precise masses. Radii can be determined relatively easily from model atmosphere analysis, absolute fluxes, and a precise distance. And we wanted to determine masses. So first of all, Sirius, brightest star in the sky, with the dA companion. You can barely see it here in this Hubble image. And we observed it 17 times with Hubble. Here's a typical observation. Oh, this has been cleaned up for public outreach. Here's a science image with the charge bleeding and so forth. By the way, you've all heard about the Hubble deep fields. This is the Hubble ultra shallow field. So in any case, and we collected all the published astrometric measurements of this Sirius system going back to 1862. It looks like this. If we take out the visual measurements and just look at photographic, CCD, and Hubble, it cleans up a lot. And if you just look at Hubble, it's really clean. The blue circles are where the Sirius B ought to be according to our solution. And the black dots are where we measured it. Zoom in, it's still perfect. You zoom way in, you start to see the observational scatter. Here's one that's off by a couple of milliarc seconds, for example. So zooming back out, here are the dynamical masses for Sirius A and B. And you see we're getting about 1% precision. Now, I can just comment that we used Hipparcos and ground-based parallaxes for this measurement. And the errors are dominated entirely by the uncertainty and the parallax of Sirius, believe it or not, which is one reason we've stopped observing. We don't need any more astrometry of the binary. Sirius B is in DR2 with and I think the accuracy of this number is probably not very good because it doesn't take into account the orbital motion. But the precision is going to be much better than the ground-based and Hipparcos. And if we put in that parallax, don't pay too much attention to the mass, but look how small the uncertainties are going to be once we have a correct Gaia solution for Sirius. So here is Sirius B in the mass-radius relation, and I plot a black line for the temperature of Sirius, and then red lines for different temperatures. These are, by the way, all the relations I'm showing are from the Montreal group from
Pierre Bergeron's very nice website. You can download all these tracks. And you see an excellent agreement with this is with a thick hydrogen layer, carbon-oxygen core, and agreeing very well with the relation for the temperature of Sirius. If you go to the HR diagram, these are cooling tracks. You can read off what the mass ought to be based on the luminosity. It ought to be 1.019, and we measured 1.018. So this worked out very well. Cooling age is given there, 126 million years. And using Cumming's initial mass-fine mass relation, the initial mass of Sirius B was around 5 solar masses with a main sequence lifetime of 100 million years. And so we know the total age of Sirius B, and we can compare that with the age of Sirius A. And I got 2 different groups, Dave Arnett and Pierre Demarque, to run models for the measured mass of Sirius A. And in both cases, they get ages of around 240 million years. And that then is very consistent with the total age of Sirius B. The gravitational redshift was discussed yesterday by Simon Joyce. I don't think he gave the actual number. So the measured gravitational redshift is 80.6, predicting the redshift from our parameters of 79.8. So we have excellent agreement. There are some puzzles. Why is there no obvious interaction of the 2 stars? The progenitor system must have been very close. How did it avoid a common envelope? And why is the eccentricity still high? I don't know. Moving on to Procyon, very similar analysis. It's a DQZ white dwarf. Far fewer ground-based measurements because it's such a difficult system. But here's the HST fit. Zooming in, once again, the blue circles are where it ought to be, black dots are where it was measured. And we did include the ground-based observations with suitable weights, or at least some of them. Some were so bad we threw them out. Those help refine the period, for example. Zooming back out here, the dynamical masses for the Procyon system. And in the HR diagram, once again, you can read off what the mass ought to be. And it agrees extremely well with our measurement. And in the mass-radius relation, it agrees perfectly with where it ought to be. If you're old enough, you remember the old iron box of 20 years ago, but our modern measurements have moved it off the iron relation and right on to carbon-oxygen. They're very similar puzzles with Procyon B, as with Sirius, no obvious evidence of interactions, which there ought to have been. Omicron Eridani is actually the original white dwarf discovered by William Enoch Fleming in 1910. And it's in a triple system, but the white dwarf orbits an M dwarf. And so we can get a dynamical mass there. By the way, it's also more famous as the home of the planet Vulcan. But the last published mass for Omicron Eridani B had been 0.43, which is, which time do I have left? Which is a real puzzle. So I got in touch with the Naval Observatory in downtown Washington, right there in the swamp in Washington. And they actually were able to, with their speckle camera, make a new measurement. And so Brian Mason and his group have refined the orbit of 40 Eridani. And here's the dynamical mass from that analysis. I better speed up here. And here it is in the mass-radius relation, 3 minutes, okay. And here we see evidence for a case of a thin hydrogen envelope. Quite good agreement with the thin envelope. And it's off by, what, 2 or 3 sigma from the thick envelope. And once again, in the HR diagram, the thick hydrogen tracks don't agree with the mass, but the thin hydrogen layer agrees very well with the observed dynamical mass. Finally, Stein 2051, my colleague Kailash Sahu realized that it was going to pass very close to a faint background star. And this gave us the opportunity to measure the deflection of the background star a replay of the 1919 solar eclipse. So here's the idea. The foreground white dwarf passes in front of the background star and deflects it. And that tells you the mass. Oh, here are the actual Hubble observations. There you see it going by the background source. And so we measured a deflection which reached the value of 2 milliarc seconds. There's the 2 milliarc second deflection. By the way, if we were in Austin, Texas, and you had an object in State College, Pennsylvania, how big an object would subtend 2 milliarc seconds? It's a United States quarter. So we have a dynamic, or not a dynamical mass, but a relativistic mass of Stein 2051. Radius determined by Pierre and his colleagues. And, oh, we made the cover of Science magazine. Not this medical thing there, but up in the corner. And we also made the top 100 science stories of 2017, according to Discover magazine. We were number 49. And here it is in the theoretical HR diagram. Expected mass 0.67, measured mass essentially the same. Mass radius relation, again, perfect agreement with the theoretical relations. So this diagram summarizes the four systems, color-coded. So each star ought to be on the line corresponding to its color. And you see that Sirius, Stein, Procyon, and 40 Eridani are all within the errors exactly on the theoretical relations. So the theory looks like it's in pretty good shape. Yeah. Oh, here's some summary points, which I won't read to you, but I'll leave up in a minute. And I'll just say thank you, and I'll say live long and prosper.
Questions?
So, Howard, there's one more puzzle. Why are all these four systems so nearby and none a bit further away? Like, do we live in a special place?
Well, there are plenty that are further away, but the further away it is, the harder it is to make the measurement.
The two closest white dwarfs are in white binaries.
Oh, well, good point. There are probably lots of other white dwarfs. I mean, Procyon, if we were a little further away, I really wonder if we'd be aware of the white dwarf.
I have a general question. You fit series B with the 10 to the minus 4 hydrogen layer, but according to stellar evolution, you expect to have a thinner layer because of nuclear burning. Actually, I read in one of Mauricio Salari's papers that he has to turn off the nuclear burning to actually get 10 to the minus 4. So
how much thinner would it be?
Like 2 orders of magnitude.
Well, I think we only compared Pierre's website gives 10 to the minus 4 and 10 to the minus 10. So that's the level of comparison we were making. So I don't know. We probably can't rule out 10 to the minus 5, 10 to the minus 6.
10 minus 4, 10 minus 6, we'll get the same. You have to go to 10 minus 10 to see a difference. So it's thicker. It's not 10 minus 10.
No, yes, for sure.
Yeah, we can rule out 10 minus 10, but probably 10 minus 6, we could live with that.
Right, so question for Howard. I did see on arXiv not a week ago where somebody analysed the Gaia sample, and they reckon they found thousands of Sirius-like binary systems.
Yeah.
Are you aware of that paper, and do you have plans for?
I'm not aware of it, but you know, this was Hubble specific, huh?
Yeah, I'll find it.
Oh, yeah. The thing is, Hubble time is so hard to get, whether, yeah.
Just 1,000.
Only 1,000. It's a question for Howard. You said a couple of times that there's no evidence for past interaction. How do you see that? Would there be a mismatch in the times?
Oh, for example, pollution of the surface of the main sequence. You know, I mean, we know that there are barium stars which have been polluted, but
yeah, I know there are quite a few cases where you don't. I mean, you don't call to be inside the envelopes of the star.
That was the other problem is that, at least in the case of Sirius, the Sirius A should have been within the envelope of the progenitor of B, and it should have spun down or at least circularized the orbit, but that didn't happen, and it's in fact still a very eccentric orbit.
Stephen, yesterday I talked about the hybrid white bulb that have an intermediate values between helium and zero white bulb. So what do you have to distinguish this hybrid from white bulb?
Yes, in theory. I mean, I haven't looked at those particular models, so I don't know where they fit. But given how good the agreement is with the helium models, I think unless there's a substantial difference between the helium ones and your hybrid ones, I don't know, but it may be possible to distinguish.
Okay, so here and then there.
This is for Stephen. Is there a special reason you focus on CRTS? Because there's, for example, Atlas now, there's PTF public data, so there's tons of treasure boxes for you to open.
Yeah, so I have looked in Atlas. Generally, it's a bit too shallow for finding white dwarf binaries. There's a few sub-dwarf systems in Atlas. PTF, yeah, we have looked there. The coverage isn't quite as dense, which makes it a bit trickier. Generally, you only find these things by having the odd dropout here or there. I mean, with your hot ones, with your reflection effects, they're easier to find, or ellipsoidal modulation, but a substantial fraction of these are just straight line out of eclipse, right? And you get 1 or 2 points that are fainter, so you need quite dense coverage.
Steven, in the middle of the Gaia white dwarf sequence that you showed, there were quite a few variables, or those pulsating spots, or those.
I doubt they're pulsating. It's tricky to see that with Catalina. That generally the uncertainty is a bit large to see normal pulsators. But, it may be spots, things like that. I know they're not strictly periodic, those variations. So, like I said, there is other issues with Catalina when you get to the lower kind of variations.
Okay, last question from Barbara here.
It's a question for Stephen. When I've used astrosysmology to estimate the masses of the hydrogen layers, and I find a very big scatter. So they go from negative 10 to negative 4 to 10 to negative 9. So that was 9.5. So how do you have any insights to explain the discrepancy in your sample?
I mean, I would say that sample is dominated by lower mass white dwarfs, and so therefore maybe you expect thicker envelopes around them. Maybe actually that the common envelope helps keep a larger envelope, perhaps. Yeah, I'm not sure.
Okay, let's thank our speakers again. Next is Solon Bauman. So our next speaker is Solon Bauman. And she's going to talk about accretion flows and boundary layers in non-magnetic cataclysmic variables using X-ray observations.
Okay, do I get that? Or maybe this is better. Okay.
No, but this is for the streaming.
Oh, okay.
Otherwise they can't hear you. That's fine.
Yeah, I do have. Okay. Stick it in there. Okay. Okay, so Thank you for the organizers inviting me to this conference. This is actually the first White Dwarf conference I've been to. And I'm going to take you a little bit off scale here into an accretion regime of more into something like compact objects. And I'm going to give a brief description of accretion flows, boundary layers, recent, and the research I've been doing for a while. And we'll try to see, try to give you an overview of what the accretion scheme looks like. May look like, something like that. Let's see. The non-magnetic CVs, I'm not going to talk about magnetic CVs here, but might make a few comments at the very end, if I have time. And they come in 4 flavors, and Dwarf, you've been hearing these all along, so I'm not going to take a lot of time to talk. So Dwarf novae, they basically you see these things in low accretion state regimes, high accretion state regimes. Basically, I will call them low states and high states. And there are 3 different types. And these are, as I described here, these are the smaller systems below the gap. And these show standstills and the UGM types above the gap with those silver outbursts and so forth. Then we skip to high state CVs. They are novel-like variables. And then basically the last systems are the classical and recurrent novae. And in generally, I kind of like mentioning the type of energies involved. This is the energy within the disk, basically some 10 to the 39 to 10 to the 40 ergs. And here you go into a regime. This is a disk instability outburst, and over here you have thermonuclear outbursts, and the involved energies are 10 to the 43 to 10 to the 46 ergs. And here we're talking about the binding energy of the envelope. Here we're talking about the disk mass. Well, the disk in energy in the disk. Okay. All right. So brief description of what the general consensus has been. The X-ray emission from non-magnetic CVs, basically, it comes from the boundary layer. It's been an old theory. It's been basic description is half of the accretion luminosity is dissipated in the disk, half in the boundary layer, and there has been ongoing work, and the latest results show modified disks where you can actually even keep optically thin boundary layers to some extent within the accretion flow in high states. But then there's a lot more work we need to do. Hope I will convince you. And then the basic regime is optically thick boundary layers at high accretion rates and optically thin boundary layers in lower accretion rates. What have we seen? This is a very difficult slide over here, so I'll just go very, very fast on it. And dwarf novae in quiescence, basically low states and high states in dwarf novae. In the X-rays, basically you see the hard X-ray emission. That's what you sort of want to know about the, so that's like a boundary layer, which is sort of optically thin. It's modeled, they are usually modeled with multi-temperaturizable and cooling flow models. These are ionization equilibrium models, collision ionization equilibrium models, but the temperatures are very high. That's something to note. And the virial temperatures in CV disks are 10 to 45 keV for a given white dwarf masses. So the thing one needs to think over here is the comparison if you do to other compact objects, which virial temperatures are extremely high, and the type of accretion flows they have. And in CVs, it's interestingly that you can easily virialize flows, and that will take them off the disk anyway, in the X-ray regime at least. Okay, and in the outbursts, the outbursts are best described with the disk instability models. You've already seen some examples, and this has been talked. And the accretion rates increase comparatively, and you expect to see the soft X-rays, but very few objects show this. The basic component you get is the hard X-ray emission still in the outburst. And there are other interesting delays and in the UV and during outburst. not much eclipses, orbital variations, but the interesting is the detection of radio emission from SS Cygni, which is synchrotron, and 5 other objects. Okay, now I'll show you some spectra for examples. I kind of like this, not that you need to see the details, just I want you just to see, this is a bunch of spectra, and Suzaku spectra. These are either quiescence or outburst. So it's not scaled, but in the outburst, the luminosities are lower, integrated fluxes are lower. But you see, it's the dominant component, most of the cases, is the hard X-ray component. So you don't see the soft boundary layers here. And more, this is a little bit older, but nice. I like this. But these are XMM data. You can see how hard the radiation is. This is actually quiescence. These are also quiescent data. But what's nice over here is the oxygen 3 Lyman alpha emission, which is mostly the prominent one. But the broadenings, the Doppler broadenings, are not more than like 700, 800 kilometers per second, which gives you velocities, Doppler velocities of the region of the boundary layers, if you really calculate that. And the line basically emission in generally in these objects are more or less about 1% of the continuum luminosity. So they don't actually radiate so much. They're not so very radiative, actually, if you look very carefully. Now I'm going to pass on this very quickly. The disk structures have been modeled with eclipse maps. And the eclipse maps that I want to, okay, the interesting thing about the eclipse mapping, and this is not eclipse mapping, but another sort of spectroscopic method on nova-likes, you don't see the observations, basically the brightness, temperature versus radius observations following standard, basically curves of the standard models. So the solid lines are standard models. These are data. They just don't follow. They are off by orders of magnitude in basically describing the flows. So there are other new methods that's been applied. One of them is the fluctuation, propagating fluctuation models that's been applied in black holes and other objects, that you can try to see the disk structure. And the interesting thing over here is that the optically thick disk has a certain signature and red noise in the X-rays. So that's like a 1/f dependence. And when the optically thick regime ends, the disk transits, and you see a break in the power spectrum. So what you expect in an integrated power spectrum, power times frequency, a flat component and a break somewhere where this transition occurs. Now we're not talking about some magnetic field break here, or this is transition of flow structure. Okay. Here is the SS Cygni. These are sort of light curves that I wanted to show. But the interesting thing I want to note here is one study that you can easily see. This is the quiescent spectrum. You see the flat component. You see the break. And during the X-ray dipping, where the optical peaks are, you see the lower X-ray emission during the optical peaks, and then you see the disk basically moving in. You see the entire, basically, the noise structure moving towards inside, and when you calculate the break frequencies where the transition occurs, basically in the peak of the outburst, it's something like 50 millihertz, then in the quiescence goes to 4.5 millihertz, and during these X-ray peaks during decline, it's around 9.7 millihertz. So you see the disk moving in and out. And the radius that these things occur is, I've actually noted there's sort of more than a few white dwarf radii. It could go out to 10 white dwarf radii. Okay, here is more of the same thing. You can see the breaks basically over here. And that's at 6 millihertz and so forth. This is outburst. You don't see a break, basically. That's somewhere around 1.1. Over here, there's WCJT. The interesting thing for you that's over here, that you see a power load during the outburst. And in generally, the hard X-ray during the quiescence is much harder, and you have very high luminosity. And you see the structure again, that the noise goes pretty in during 6 days after outburst, and 30 days after you see the optically thick disk move out to 1 millihertz. I have to pass on this, but the only interesting thing over here is more, this is quiescent and outburst spectrum of Z-Cha, and you can easily see the hard X-ray emission during the outburst, during quiescence, and there is some soft X-ray emission as you can detect, as one can detect, 24 to 40 eV. This is something I'm going to finish, and the luminosities in the X-rays, in the X-ray regime is slightly low, but temperatures are higher. And in both cases, in 3 sigma, you can find a power law component in the spectrum. In generally, I will pass on this, but then when you look into the RGS regime in the XMM data for the line emission, you can easily see that the resonance lines are not there in quiescence. They appear in outburst, but it looks like the entire regime, the plasma is in a non-equilibrium ionization state, more or less. Here's a collection of spectra, power spectra. In quiescence, you can always see the optically thick part and the breaks in all of them. This is UV spectra and so forth. There are also lags, which tells us that this is a standard lags that you see in also compact binaries between UV and X-rays. These are not like soft lags or hard lags. And in nova lights, when you go to hard X-ray regime, okay, I'm very, very good at not giving proper talks, so I knew this was going to happen, but then I wanted to cover a lot of stuff, and it's always like this. Okay, so nova lights, you know, they're a hard X-ray regime and very high accretion rates. There are several objects there. These objects have winds, and you expect at high X-ray regime to see the boundary layers that are optically thick. They don't exist, so no black body emission really has been found. And these are very, again, hard X-ray sources. It has been the case overall observations. They have the hottest white dwarfs, and compared to, for example, polars and stuff at the same orbital periods, they are about 3 times hotter than polars at the same, basically, orbital periods. And some of them have been observed as radio sources. We have actually observed some and have concluded that these also can be explained in the context of a regime where you have non-equilibrium ionization flows that are virialized in the disk. They are ADAF-like structures, and basically the part of the inner disk, the energy is immersed in the disk, is basically absorbed in the flow. It's within the flow. It doesn't radiate, and it's advected into the white dwarf. And the white dwarfs start getting hotter. And the X-ray regime is always very inefficient due to these advective flows. In any ways, these are some newer work that we're doing. And I just wanted to show, this is, for example, at the iron line, these are new star data. This is Swift plus new star data. The only thing I want to show here, this is the standard collisional equilibrium model that needs to be fitted to the data. In general, if in the consensus, it basically is not inconsistent. And when you apply a non-equilibrium ionization model, perfectly models the iron line. Over here, the same problem exists. This is, again, collisional equilibrium analysis. This is more complex analysis. This is in progress. So I never have time for this. I always have to skip typics. So the typics is, you can read it in the paper if you like. And the main idea here is that you increase the accretion regime even more into m dot which is something like of the order few times 10 to the negative 8 solar masses, and you can get interesting regime where if you dump so much energy, because the efficiency goes so low that if you heat up the white dwarf with a very high, basically imparting a lot of accretion luminosity in it, you can actually trigger a thermonuclear runaway. So, thank you for listening and keeping up with my pace.
We're going to have one more speaker for questions.
Okay, you want to take that out?
Edward, sign up. Keep it here like
okay.
Excuse me. Point from.
And the pointer? Oh, okay. Okay. Well, my talk is going to be on cataclysmic variable white dwarfs. There have been quite a bit said about these at this conference in posters and in talks. My principal collaborators on this project are Patrick Godin, who's a research associate at Villanova. He's worked with me for a number of years, and also Joanna Miklaszewska of the Polish Academy of Sciences. So let me start with a slide, just is a quick rundown on the organization of the talk. I'm going to be spending time on the photospheres of accreting white dwarfs when they're exposed, the mix of elements and the relative abundances, the nitrogen to carbon anomaly in CV white dwarfs, and then the exposed accreting white dwarfs in related systems, for example, CQ draw. We now have evidence that this is not a normal symbiotic star with a white dwarf and a red giant, rather it's a triple system, and I'll show you evidence for that. And then RW Hydri is another S-type symbiotic star in which there appears to be no accretion disk. It's simply a bare accreting white dwarf, accreting from the wind. And then I'll end up with two very interesting cases of CV white dwarfs where we see evidence of thermonuclear ashes on their surfaces. And that is VW Hydri, and most recently, the white dwarf in U Geminorum. So let me just start real quick here with, well, for single white dwarfs, you all know the processes that one has to deal with. But now think of a cataclysmic variable white dwarf where you have compression, you have advection, you have accretion, you have a continual source of high energy photons shining into the white dwarf. So there are a lot more, there are many more complications in studying CV white dwarfs than in normal white dwarfs, in non-accreting white dwarfs. Just to emphasize that for some of you. So this is just a pristine DA white dwarf, and no debris disk accretion, no interstellar accretion, and you simply see the Balmer lines. Let's go to the next slide. And here is a CV white dwarf. This is one of the first ones exposed. This is a VW Hydri white dwarf, and you can see that its atmosphere is laden with metals. Moreover, this is really a two-temperature system, where this is one of the first Hubble spectra of a CV white dwarf. I think it was 93 this was taken. We published this in 95. But you can see here strong absorption lines of accreted metals. And moreover, you can see that this is a two-temperature white dwarf. You can see here that we have an accretion belt whose signature is given by this, the dots right here. And then the white dwarf itself, you can see its spectrum up here. And so this is really a two-temperature white dwarf, and we consider this to be the first evidence of an accretion belt as envisioned by Kippenhahn and Thomas in 1978. Now it's now called a spreading layer, but we think that if you had just a single temperature white dwarf without this accretion belt, this right here would be a straight line, absolutely straight. So you really need two temperatures to explain the spectrum of the VW Hydri white dwarf. Let's go to the next slide. Whoops. And this is U Geminorum. This is a fused spectrum that was in the archive, the NASA archive at MAST. And you can see here with fuse, you're really probing the deepest innermost layers of the disk and the white dwarf photosphere. And here again, you see in U Gem here's the Lyman limit. You can see that in UGEM, again, you're laden with accreted metals in this system. And let's go on to the next slide. Just to tell you what tools we use, we're strictly basing our analyses on T-Lusty and SynSpec, the latest versions. And our steady-state accretion disk models are done with DiskSyn, also from Ivan Hubany and collaborators. We can include accretion belt models, accretion rings, and accretion curtain models in our analyses. And we also now have been producing non-standard disks where you have an arbitrary T of R radial temperature distribution in the disk, and we're also including the contribution to the UV of a boundary layer. So we not only use the Wade and Hubany steady-state disks, but we calculate our own disks with all kinds of modifications and newer input physics. Let's go to the next slide. And just to give you some quick example, this is a stiff spectrum of the white dwarf in the constellation Mensa, TU Ben, and of course you can see lots of absorption lines of accreted material in its atmosphere. Another example, real quick. This is a stiff spectrum also published in 2008. Again, just to acquaint you with the fact that we can see these accreted atmospheres very easily. And here's one of those beautiful examples where we have a marriage between fuse and HST stis. And here you can see that we have clearly a white dwarf in SS Aurigae with a temperature of about 34,000 degrees. We actually found the white dwarf with IUE early on, and but of course did not go down to the Lyman limit, and the temperature was a few thousand degrees different. Basically, you're seeing the white dwarf in SS Aurigae. Now let's go to the next slide. And this is Anapala's diagram of white dwarf effective temperature versus orbital period. These are the accretion rate scales corresponding to for various white dwarf masses, and you can see that above the period gap, above the 3-hour upper bound of the period gap, it's rather sparsely populated compared to the white dwarfs with accurate effective temperatures below the period gap. Let's go to the next slide. And this is one of the objects from a large GEO program that we had with Boris Ganska as PI. This is CW Mon, where we don't have exactly a completely exposed white dwarf. There is some disk contribution. Oops, sorry. There is some disk contribution, and that's the dashed line here. The white dwarf itself is dominating the light, but of course, to extract abundances and rotation rates and so on, it's a little trickier when you have the disk or boundary layer still contributing. Let's go to another slide now. And so we have this nitrogen carbon abundance inversion in cataclysmic variables. Every CV white dwarf, not everyone, but many of them, have this very, very strong nitrogen abundance and nitrogen lines in absorption and in emission, and very weak carbon, underabundant carbon, which is a signature of hot CNO burning. And according to Boris, about 10% of the cataclysmic variables show this anomaly. And I don't know if that number's changed or not, but it's still the same. Yeah, okay. So we see here then a number of systems that show this anomaly. The emission lines almost certainly arise from the accretion disk or boundary layer that forms when the Roche-Loeb filling donor secondary transfers gas to the white dwarf. But this anomaly has also been seen in magnetics and also in one AMCVN system, CE315. So this anomaly is seen in a number of different types of cataclysmic systems with white dwarfs. Now let's go to the next slide. The origin of the anomaly, is it a formerly more massive peeled down donor, or is it the accreting white dwarf itself that has produced this kind of anomaly? And one argument that we make is that the accretion of this CNO process material by the secondary during a dynamical nova shell ejection is probably minimal. However, following the dynamical ejection of an envelope in a classical nova explosion, you have the white dwarf is bloated, and you have what we call a brief common envelope stage, where the secondary is actually orbiting inside
the envelope of a bloated white dwarf, or very close to the bloated envelope of the white dwarf, and therefore pollution occurs, contamination occurs on the secondary. Then the secondary donor can transfer that material back to the white dwarf. I'll come back to this point in a minute. Well, here are the abundances that we have for several CV white dwarfs. We see that aluminum is elevated in a number of them. Here is, we see that twice solar aluminum in VW Hydri. UGM Minorum also has 20 solar aluminum. It's not up here, but 20 solar of aluminum in its atmosphere. And here are 3 that were analyzed by Boris, each of which, these are SU UMA systems below the period gap. And you can see that they all 3 have elevated aluminum. These 3 white dwarfs are relatively cool. Therefore, you can dismiss radiative levitation as being responsible for the aluminum overabundances. So something else is going on in the envelope. We also have possible cases with SS Origi, which has elevated nitrogen and underabundant carbon. WW SETI, which also has underabundant carbon and elevated nitrogen. And RU PEG, I'm going to say more about it, with underabundant carbon and elevated nitrogen. Let's go to the next slide. And we see here, these are just a rundown of abundances that have been determined for these objects. Again, just you can see here that silicon is elevated. You see, silicon in UGEM is sometimes measured to be 6.6 to 10 times solar in UGEM. More about that later. And we go on to this next slide. Now let's go to systems that are not really what you think of as normal CV white dwarfs, but something strange is going on. This is the old NOVA RR PIC, Nova Pictoris 1925. And these are 4 fuse sub-exposures. These were in the massed archive, never having been analyzed. And let's go to the next slide. And we see that if you try to fit an accretion disk to the fused spectrum of RR PIC, look what happens. These absorption lines are not at all replicated. You can see that here, you see it's just almost a straight line across here with an accretion disk fit. Now let's go to a photosphere fit. It doesn't fit very well, but you account for these lines. At least it appears that these lines can be reproduced by photosphere. That doesn't mean their origin is in the white dwarf photosphere. But where do these absorption lines come from? That's a major puzzle right now. And if you assume that they're from the photosphere, you have great overabundances of things like phosphorus, which is right here. This phosphorus line, sorry. Okay, you can see right here that phosphorus, if this were a photospheric feature, phosphorus would be maybe 50 or 100 times solar abundance of phosphorus. Let's go to the next slide. CQ draw. We now have evidence that Dieter Reimers was correct. Excuse me just a second. That Dieter Reimers was correct, that it's a triple system. And here's why we think this is the case. CQ draw, according to Augustin Skopal and his workers in Slovakia, they say it's a normal symbiotic variable with a red giant and a white dwarf. We think not, and I'll show you why in the next slide. Here is RU PEG in quiescence. Most of the light here in quiescence is contributed by the accreting white dwarf. Here is CQ draw, okay? And you can see kind of a close correspondence between RU PEG, a dwarf nova, and CQ draw. Let's go to the next slide. And here is fuse. Look how much agreement there is between the IUE spectrum of RU PEG and CQ draw. So we now think that it is a triple system. Let me just hurry. RW Hydri, this is the one that we think is a bare white dwarf with no evidence of an accretion disk and no optical outburst ever recorded. It's a 160,000 degree white dwarf. 160,000 degree white dwarf. The temperature, it's the first time that the temperature from a non-LTE model atmosphere fit agrees with modified Zanstra methods. Normally, these symbiotics use modified Zanstra techniques, but with non-LTE model atmospheres, we can account for this. Finally, and this is really to me, the icing on the cake. I know last night we heard about all of us being a family, so I don't think anybody's going to scoop us on this, but so I decided to show it. And, you know, this is a study of U geminorum using HST codes with the short wavelength setting at 1050 angstroms. So you go right down to the Lyman limit. Well, we saw elevated aluminum. We knew that from before. But here's what shows up that just totally surprised us. And that is argon-3. It tracks the white dwarf. It tracks the motion of the white dwarf. It's almost certainly photospheric. Now, where in the world would argon-3 come from? The only way you can make argon-3 in a classical nova explosion is if you have a massive white dwarf. U geminorum is 1.1 to 1.2 solar masses, somewhere in between. We find that the argon abundance is at least 20 times solar in abundance. Therefore, the only way to make argon in a classical nova with hot explosive CNO burning is if you have a massive white dwarf. A carbon-oxygen core will not do it. You have to have an oxygen-neon-magnesium white dwarf. So you're hearing here for the first time that the white dwarf in the prototypical dwarf nova, U geminorum, is an oxygen-neon-magnesium white dwarf. And we're just now in the process of writing this up and everything, but we're just very excited about this. And okay, so I guess I'll just put up the this is sort of a kind of a summary of what we've done. So anyway, thank you very much.
Anything like 2 questions? There.
I don't see how pollution by novae could possibly explain the N over C abundance anomalies, because you just can't put enough material onto the secondary to drown out the secondary's original abundance, can you?
Well, if there's a radiative layer above the convection zone in the donor, you could. You wouldn't always see it. You wouldn't always see it. It would mix.
Yeah, but most of the end also pretty convective. I mean, you're really going to dilute it, though.
Yeah, but as I say, if there's a radiative layer above that convection zone, you can catch it. The pollution of it.
Why would that be?
Because it hasn't settled into the convection zone yet.
Any other questions? There.
Are these abundance measurements sensitive to the outburst phase? So quiescence versus outburst?
We've looked for that. In fact, that was the motivation for the UGEM HST COES experiment with Mike Shara. We were trying to see diffusion, and it's not clear. I mean, overall you can see a reduction in the overall metal abundance, Z, but if for individual elements, it's not clear.
Any questions? Let's thank the speakers then.
Thank you very much.
So they pay attention.
Do I hold it like this or like this? Or?
I mean, the cold.
Sure.
Well, I figure the elder people can put it here. And, well,
Yeah.
Okay, everyone, let's begin the next section with a talk from Matthew Green. Gaia 14, the first fully eclipsing AM campaign.
Okay. So, hi everyone. If you need me to move the microphone closer or further away, please just shout out. So my name is Matthew Green. I'm a PhD student at the University of Warwick, where I work with my two supervisors who are Tom Marsh and Danny Steegs. And today I'm going to be talking about these AMCVN type binaries, and in particular about Gaia 14 AAE, which, like the title says, is the first AMCVN that we know of where the central white dwarf is fully eclipsed. So AMCVN binaries are ultra-compact accreting binaries. They're related to cataclysmic variables, and they have a similar structure to CVs in that they consist of a central white dwarf, which is accreting material from a donor star, which accretes via an accretion disk in most cases. There's two sort of key things that distinguish AMCVNs from CVs. The first is that they have very short orbital periods. So in the orbital period distribution of CVs, AMCVNs lie down here at the shortest period end, below the period minimum of hydrogen accreting CVs. The other key distinguishing factor for AMCVNs is that the material that's accreted consists mostly of helium. So it's hydrogen deficient, and in almost all cases, there's no detectable hydrogen at all present. So those two things together suggest that the donors in these systems are some sort of very dense and helium-dominated sort of evolved object. The exact nature isn't clear. It could be another white dwarf, or it could be some other sort of helium-burning star. We'll come back to that question in just a moment. So since this figure at the bottom was made, which was 2002, the number of AMCVNs has shot up from around a dozen to about 50. That's mostly because of surveys such as SDSS and transient-based surveys like PTF and ZTF. Within the AMCVN population, we have a general trend that there's a lot of systems at long orbital periods, so around 50, 60, 40 minutes, and much fewer systems down at the sort of 5-10 minute period end. So apart from being interesting in their own right, one of the things that motivates interest in AMCVNs is that they're quite loud sources of gravitational waves in the frequencies that LISA will detect. So this figure has been shown before in the conference. It's from a paper by Thomas Kupfer. And this is, all the data points that are shown here are sort of proposed LISA calibration systems. So these are known binaries that are within our galaxy that we'll be able to detect, that we think we'll be able to detect with LISA, and that we can use the properties, as long as the binaries are understood, we can use their properties to test how well LISA is calibrated. And all the black points here are AMCVNs, so you can see of these sort of proposed calibration systems, they make up quite a large percentage. One of the big mysteries for AMCVNs is how the systems form. There are three sort of proposed formation channels. It's generally thought that it could be perhaps all three systems contribute, but the percentage that each system contributes to the population is a question of interest. The formation channel that's generally got the most press is this first one, the white dwarf donor channel. This is where the AMCVN descends from a double degenerate binary. The other two, either the donor is a helium-burning star or the donor descends from the donor in an evolved hydrogen CV, so a CV where the donor is evolved. Both of these, the donor is a little bit hotter because it has some fusion going on at the point where mass transfer starts, and so the donor has a little bit more thermal support, it's a little bit more puffed up. So if you can study the donor, you can hopefully distinguish between systems that form by those three evolutionary channels. Unfortunately, the donor is the faintest part of the system, which makes it quite difficult to study directly. There's almost no AMCVNs where we detect the donor directly. If you are able to study the donor, you can compare the properties that you measure for it with theoretical models like the models that I'm showing here.
So this is a plot of donor radius against donor mass. The black lines, just concentrate on those for a moment, those are evolutionary tracks with 4 white dwarf donors. So a donor evolves from right to left across the diagram as it loses mass, following these red arrows. The dashed lines that I'm showing above, those are models with helium star donors. So the radius is a bit larger for the same mass because of that thermal support. And the tracks coming down from the top here are evolutionary tracks descended from evolved CVs. On the same plot, we can plot lines of constant mean density of the donor, so they effectively correspond to lines of constant orbital period. So for a system of a given orbital period, if you're able to measure the donor radius or the donor mass, you can constrain how degenerate the donor is. So if it's low mass and low radius, it'll be down here as a sort of very degenerate white dwarf. Whereas if it's higher mass and higher radius, it'll be something more like a helium star or an evolved CV if it's a longer orbital period, so something with more sort of thermal support in it. So the fact that we want to study the donors in these systems brings us to eclipsing AIM-CVNs. There's only 2 eclipsing AIM-CVNs known, and of those, only 1 is a fully eclipser, and that's the system that I've been studying, which is Gaia 14AAE. So Gaia 14AAE was discovered in 2014 by a Gaia Science Alert. It has an orbital period of 50 minutes, which puts it here at the long end of the AIM-CVN population. So this is the most populated end of the distribution. And it's magnitude of 18.5, which makes it quite faint and a little bit tricky to study. So we followed up the object with a couple of high-speed photometers, UltraCam and Chimera. We obtained in total about 50 eclipses, which we can phase fold together to produce light curves like the one that you can see here, and hopefully the people at the back can see it okay. So in this light curve, the strong central feature is the eclipse of the central white dwarf as the donor passes in front of it. This fainter feature that follows that eclipse is the eclipse of the bright spot as the donor passes in front of that. And the bright spot is the point where the stream of accreted matter hits the edge of the accretion disk. So you can fit a sort of geometric model to the shape of this light curve, and you can use that to constrain the mass and radius of the 2 stars. And that gives us our donor mass and radius that we can plot on the figure that I showed you a couple of minutes ago. So for Gaia 14AAE, you can see that the mass is unexpectedly high, is higher than you would expect if you were to assume that it was a degenerate donor. So it lies in this region of parameter space. It's a little bit difficult to distinguish between evolved CV models and helium star models. There's advantages and disadvantages to the 2. In particular, the disadvantage of the evolved CV track is that it's quite difficult to explain the complete absence of hydrogen by that model. But the key thing that we can say is that it definitely doesn't seem to be a white dwarf donor. And that's as opposed to the partially eclipsing system YZ LMI, which I'm also showing for comparison. So the mass, the donor mass of Gaia 14AAE is higher, like I said, than you'd expect if it was degenerate. If it was degenerate, you'd expect a mass of around 1% of a solar mass. We get about 2.5%. And so that means the gravitational wave emission strength is higher by roughly a factor of 2.5 as well. And that means in turn that the volume over which you'd be able to measure Gaia 14AAE is larger by about a factor of 20. So that's quite significant from a gravitational wave perspective if you're interested in detecting AIM-CVNs. So we'd like to say whether this is true sort of across the AIM-CVN population. For that, we need to look at a larger sample of AIM-CVNs. And for that, we need to look at a couple of other methods for measuring the masses in these systems. There's 2 other key methods that have been used. Both of them have disadvantages for AIM-CVNs. Spectroscopy is limited by how faint most of the systems are and by the fact that they have short orbital periods, which means you need shorter exposure times if you're to resolve the orbital phase. We also see a lot used the super hump method. I won't go into too much detail about how the method works, but it's an empirical method that was derived for hydrogen CVs. It's not entirely clear that whether it will work quite so well for helium accreting systems. And so the masses that we measure by that method, which are gray points on this diagram, need to be presented with something of a health warning because of that. So on this figure here, I'm plotting the mass, the donor masses of every AMCVN for which there's some measurement of the mass ratio. Where we only have a mass ratio estimate, I've assumed an accretor mass of 0.7. And the gray points are superhump derived masses. The green points are spectroscopic derived masses. And you can see that across the population, the general trend seems to agree with the two eclipsing systems that I showed earlier, that all of the donors in these systems are quite inflated. So none of them are cold white dwarf donors. We're not necessarily saying that none of them are white dwarf donors at all. A lot of these systems could agree with hot white dwarf donors. And it might be that in the models we might have underestimated some process that can heat up the donors in these systems, perhaps irradiation by the central white dwarf. But what does seem to be the case is that for all of them, the donor is not degenerate, the donor is higher mass than you would expect if you were to assume it was degenerate. So the conclusions that I'll leave you with, we've looked at the first fully eclipsing AMCVN. We've measured the mass and the radius more precisely than has been done for any AMCVN to date. We find that the donor is not a degenerate white dwarf, which means its mass and therefore its gravitational wave emission are both higher. And we find sort of a suggestion that across the AMCVN population, this trend might also be the case. So thank you. And just before I finish, I just want to add that my PhD ends quite soon. I'm just starting my final year. After that, I'll be looking for a job. So please come and talk to me. Thank you.
We're going to have one more talk with more questions. So the talk right now is going to be from David Wilson, White Dwarfs as Tracers of M-Dwarf Stellar Winds.
Hello, yes, I'm Dave Wilson. Most of the work I'm going to present today I did at the University of Warwick, but I've recently moved to here, which incidentally means for the 3 I've been to, where am I is a better tracer of where is the White Dwarf workshop than is it in Europe. Did this work with Boris and Odette, who are here, and also Jeremy Drake at SAO. I'm actually moving here to do M-dwarfs rather than white dwarfs, so perhaps fittingly I'm going to talk about M-dwarfs and white dwarfs. So starting off with why are we interested in M-dwarfs? Well, why am I interested? Some people are interested in them for their own sake, but I'm interested in them because they are by far the easiest place to find Earth-like planets. I've put lots of inverted commas in these in that phrase because all those statements will cause arguments in exoplanet meetings. But the broad situation is that M-dwarf habitable zones, so roughly where liquid water can exist on a planet's surface, are much closer in. So the planets there have much shorter periods, so much easier to find. Because those planets are much closer into the M-dwarf, the effects of stellar activity, the space weather environment those planets undergo, might be very different to the Earth. And in particular, the stellar wind of the M-dwarfs is very uncertain, simply because it's very hard to measure. But we can measure it using white dwarfs. And in particular, if we replace that planet with a white dwarf, that white dwarf is experiencing a very similar space weather environment to a planet around an M-dwarf, but in this case, it's detectable. I was trying to search for a decent artist impression to show this. Fortunately, the dinner yesterday gave me the tools I needed. So this is a post-common envelope binary. So we've got a M star and a white dwarf that are in an unresolved binary, but not so close to that mass transfer is occurring. So talking periods of a few hours to a few days. And just to, Evan gave a nice overview of the accretion diffusion scenario yesterday, Wednesday, but to recap, because it will come up in the next few talks as well. White dwarfs, as probably all know, have very high surface gravities, so materials, any metal that isn't hydrogen or helium, diffuses out of their atmosphere on very short timescales, so that if we see any extant metals in a white dwarf spectrum, it has to have been accreted after the white dwarf formed, and for shorter timescales, it has to be accreting at the moment. So in most cases, when we talk about this, we talk about it in the context of accreting planetary debris. In this case, we're accreting the stellar wind from the M dwarf. So if you take a spectrum of the white dwarf, look at the absorption lines in there, add a model atmosphere, and then we get the accretion rate onto the white dwarf, we can scale it up over the geometry of the system to infer the stellar wind from the M dwarf. In most cases, this has been done before in the opticals, so you really only get calcium. So ideally, you want to go into the UV to get both more elements, so you can get a better idea of the total accretion rate onto the M dwarf, and also do the chemistry of the stellar wind. So that's what we did. Last year, we awarded a Hubble Space Telescope XMM time to observe 12 systems simultaneously in the X-ray and in the UV. Don't have time to go into the X-ray observations in this talk. And we also had 3 more systems that we added in from previous programs. Those observations finished on Sunday, so I think this is the most recently obtained data we're going to see in the conference. There's a Sunday spectrum. Yeah, it's a white dwarf. But interestingly, on this one, if you zoom in a bit closer, you can see it's magnetic. And now you've all analyzed the spectrum for as long as I have. So moving on, this is my favorite spectrum of the program. This one was actually significantly cooler than we expected it to be. So in this case, we have absorption from the M dwarf stellar wind onto the white dwarf, but also emission from the M dwarf itself poking up above the white dwarf spectrum. Now, if they're all like this would be a pain because it makes them more difficult, as Stephen was talking about, to subtract off the M dwarf. But in most cases, the white dwarf flux is much greater than the M dwarf. And typically, they look something like this. So you see a nice, clean white dwarf spectrum filled with loads and loads of metal lines. Usually see silicon, oxygen, and carbon, and then occasionally sulfur and perhaps nitrogen. And so the results so far, we've observed 13 M dwarf, white dwarf binaries. We also observed a white dwarf, brown dwarf binary. We observed them, and 11 of those were simultaneous observations with XMM. In 11 out of 13 of the systems, we have clear detections of wind accretion onto the white dwarf. The 2 that don't are a bit of a mystery because there are orbital periods where we have other objects that do show accretion. So why those don't show accretion is an interesting question. 2 of the systems, for various reasons, we observed twice, so we can have a look for variability, see if the stellar wind changes over time. And we've had time to measure the accretion rates and do a model atmosphere fitting 3 of those. So I'll show you where those fit in with the state of the field. So this is before the program. These are measurements of M dwarf stellar wind strength against the spectral type of the M dwarf. And these are almost all using this technique of using post-common envelope binaries. I think that one there is the only one that's been measured at a star on its own. And comparing these to the solar value, they're scattered all around the solar value. There's no real trends there between spectral type and M dwarf wind strength. So you add in our new 3, they're all pretty much on the solar value. And so that's our first result. Consider, again, the scenario at the beginning. We're looking for this in the context of habitable planets. If the stellar wind strength at the M dwarf is as strong as the sun, and the planet is much closer, the stellar wind at the planet and any habitable planet around an M dwarf is experiencing is much stronger than the Earth. When we finished, this will be where all the others go. So we're pretty firmly blanketing the kind of mid-range of M dwarf spectral type. So we'll be able to do a really good analysis for these mid-type M dwarfs of wind rates compared with spectral type, and also because we know the orbital periods, and to assume the M dwarf is tidally locked, then the spin periods we'll be able to do wind rates against spin period. We are missing almost completely early type M dwarfs and late type M dwarfs. That's because there's simply less targets available that were accessible with HST in one orbit. As I said, we can also look at the chemistry of the wind. So this is where these three objects we've analyzed so far come in chemically. We've got oxygen and silicon against carbon and silicon, compared here with the sun and with the Earth. And you can see they are vaguely similar to the sun, a bit less carbon, a bit more oxygen, but certainly much more similar to the sun than they are to the Earth. So certainly accreting stellar wind material rather than rocky material. Now, I know Jay gave us a very inspiring talk on Wednesday about how we should all be interested in planets, but even if you don't like planets, then this sample has uses beyond that. We made sure that we were covering a very wide range, or as wide a range as we could, of white dwarf effective temperatures and orbital periods. So we can use these for studying things like CV evolution, angular momentum loss, and also be used as calibrators for models of diffusion and radiative levitation. So I'll conclude there, and thank you very much.
Questions? Okay, so I saw her.
So, David, could you say something more about the one that has a magnetic white dwarf? What is its orbital period, and does this help with what Lily was saying, the evolution systems of magnetic dwarfs?
So I can't say much more than saying we got the spectrum a while ago, and the orbital period is, I think, about half a day.
Do you have a field strength? Or?
No, we haven't got that quite.
Yeah. I think it's for you because you already.
Yeah, regarding the Gaia and that object, is there any chance that this could be observed with costs on HST? It'd be really nice to get a UV spectrum and you get the time tag light curve information for free.
I agree, it would be nice. I think we had a proposal in it for it the last year. Unfortunately, it was rejected. I think we're planning to apply again this coming year. So, fingers crossed.
We had the hand and then three and then.
This is a question for David. Essentially about just the effect of the white dwarf on the M dwarf.
Yeah.
Like, do you have enough dynamic range of kind of irradiation that you can see if there's any trend with how irradiated the M dwarf is?
Well, I thought that aspect of it. Possibly, yes. Yeah, the orbital periods are pretty spread out. So I'd be surprised if there wasn't an effect, but yes, we could definitely look at that.
For the, do you know the range of ages of your systems? And can you extrapolate to younger systems where maybe the wind is stronger?
Yes, that I think is a very interesting question of how there is a well-known activity-age relationship with M dwarfs, but because these systems are being gone through a common envelope, I think we need to model how or if that process changes the activity age of the M dwarf. It certainly doesn't change the chemistry of the M dwarf, as far as we can tell, but yeah, I think that's something that needs to be done before we can bring out an age activity relation.
Okay, there and then, yeah.
So for David, the pollution calculations for the surface of the white dwarf and these systems, I think, correct me if I'm wrong, but I think they're pretty different because your accretion is dominated by
having hydrogen and
Yeah.
helium. So can you maybe just comment on how much that changes the calculations, or are there uncertainties associated with? Because in the classic collision calculations, you either have a pure hydrogen or pure helium background.
So far we've just, we haven't really considered the hydrogen and helium. We've just taken the measurements that we have of the elements that were there and scaled them up to the solar values. But certainly, yeah, adding in hydrogen and helium, seeing if that has an effect. We've got, the hydrogen helium is very large compared to the metal ones, but it's still relatively small in terms of atoms per surface area. So I'm not sure if it will have that much an effect. But yeah, we're looking into.
David, do we expect the abundances in the winds to actually reflect the abundances of the end dwarfs, or will there be some fractionation between the others?
Yes, but it's small. I think there are measurements for the solar wind versus the solar photosphere, and there are differences, but not so much that we might change the results.
Could you comment about the X-ray emission in this binaries? Is it to the accretion or to the wind?
So the X-ray emission will almost certainly be dominated by the end dwarf. I haven't done much on the X-ray yet, but you can get at least limits on stellar wind from the X-ray emission from the end dwarf. And in one case where it's been done at different epochs, the measurement from the accretion onto the white dwarf and the X-ray emission from the end dwarf has returned very different values for the stellar wind. And that's done at different epochs, so that's interpreted as a change in the stellar wind rate. But because we've got simultaneous data, we'll be able to do this now and see if that holds up. If we get the same or different values for the X-ray and UV wind rates.
Okay, so let's thank our speakers again. So our next speaker is Roberto Rosa. She's going to talk about how is the disrupted planetesimal and the pulsating white dwarf G2938 accreted.
Sorry. Let me put it here. Okay. Oh, it's cold. Oh, sorry. Okay. With this, I go front and what is here? Okay. Okay. Hello, everyone. Everyone listen very well. Okay. I'm Odette. I am in Warwick. Today I'll be talking about how the disrupted planetesimal in the pulsating white dwarf G29-38 is accreted. So G29-38 was discovered with another system that it has a very similar name. I don't know why, but nobody cared about that discovery because it was just two more members that were joining to the pulsating white dwarf family. So nobody cared about it. And then everyone was paying attention to the system because it was infrared excess. So how the infrared excess was explained, it was just dust, emission of dust. So if we have just a white dwarf, this is the shape that we will have of the spectral energy distribution. However, if we have a disk that has a gap between the star and the disk, we will have this shape, which is more what we see for G29-38. So the dust was explained by the disruption of a planetesimal that was passing close to the white dwarf, was disrupted, it formed dust. And this dust accrete on the white dwarf, and therefore what we see on the spectroscopy of the white dwarf is that their absorption lines correspond to metals. So then this is very cool because if we can measure the abundances of the white dwarf, then we can get insights, ideas of what is the planetesimal, the nature of the planetesimal. So how do we do this? So this is a white dwarf modeling. So there are quite a few codes around, but the one that I'm using is a Coster et al. So it has all these assumptions, but I will going to focus in this one here because it was also used in the other codes. It depends on the effective temperature, the surface gravity, and what we care about, the composition. But when you integrate with all the angles to get the white dwarf model. One of the assumptions is that the metal distribution is homogeneous across the white dwarf surface. But is this the case? So there are a few words where they are trying to test this. Just look at the variability of the calcium line, mapping the calcium line in the white dwarf surface. So we want to also test this. And why I'm thinking that it might not be homogeneous, because if we bring some insights from cataclysmic variable, especially dwarf nova, we have low accretion. Dwarf nova is a accreting white dwarf, that is accreting material from a low mass companion. It forms the disk, and then there is accretion of the white dwarf. So one of the scenarios is this one that I have on the left, where you have the disk, there is a corona here, and the metals accrete on the white dwarf. There is another one where you have the disk, there is a corona that is formed here, and because of evaporation, so you have accretion above and below of the disk. So if you have the former, the accretion, or the metal will be more concentrated in the equator of the white dwarf. Whether in the second case, the distribution will be more homogeneous, which is what we would like to have. So if you have homogeneous, so what I'm going to test is like, I'm going to assume that the metal distribution is homogeneous. So if we have the ideal case that you have a spot on the white dwarf where you can measure the abundance in this region, and also you take a different region, you measure the abundance in these two, and then you compare both, you should have the same abundance in case the metal distribution is homogeneous. So what it was ignored at the beginning, that it wasn't attractive, that the white dwarf was pulsating, now becomes a very important tool how to test this. So here I'm showing a modeling of one of the light curves for this period, assuming these modes, where if you have, you have two states, A and B, and this is the situation that you will see if it's in the minimum of the light curve, where you see the intensity is a bit more even across the white dwarf. But if you are in the peak of the light curve, you will have a region that is hotter, but it's very localized. And since it's hotter, also the flux that comes from this region dominates the spectroscopy of the white dwarf. Therefore, the spectrum that we're going to see is a combination of the flux coming from this cooler area and this hotter area. So this is what we're going to do. We're going to try to get data, get this state, measure the abundances of all across the white dwarf, and also measure the abundances in this area. So we need light curves and get spectrum in this moment and in this moment, but we didn't have to apply for any time because it was already data available. So we have 4 orbits with time series spectroscopy, which is good because we can get the light curves, and therefore we can get the minimum of the light curves and the peaks of the light curves. And then I just need to look in the literature, because this is a very well-studied system, and there are a lot of works that have been measured the effective temperature and the surface gravity, but then I have all these measurements, I didn't know which one to choose. So then I said, okay, I need to get at least these parameters, I need to do something, but if I pick one, then maybe some of the other people will be angry because I choose one and prefer the other. And then how I did that, I'm going to show this again. So if you have this situation, then you can measure the effective temperature and the surface gravity, and the surface gravity will give you a larger radius. So you will have like more, like an underlying white dwarf. So I built a spectrum. It's not very clear here, but here in the minimum, you have a blue, and you get the spectrum just combining the counts that are in the minimum of the light curve. And this is what you have. I tried to fit that using the scaling factor, the white dwarf model that includes the effective temperature and the surface gravity. However, if you just fit a spectroscopy in the ultraviolet, you have this correlation between the effective temperature and the surface gravity. So whichever solution that you try to pick in this value will give you a very good fit. So to break this degeneracy, I'm using the scaling factor, which depends on the radius and the distance. This is a good occasion because at least I have to mention Gaia in this talk at least once. And the radius from the mass radius relationship for the A white dwarf, and to constrain the slope of the model in the optical, we got ultracam photometry. And since I'm trying to fit the minimum spectrum, I also repeat the same idea in the optical wavelengths. So then I fit that, and this is what I got. So I finally constrained the surface gravity to about 8, and the effective temperature was 11,000. Then I move on again to try to measure the surface abundances. The abundances. So this is what I had before. So if we measure the abundances in this spectrum, then we will have the abundances on all the surface of the white dwarf. But if we pick the different peaks and you build the spectrum, what you are having is something like that, because there are a lot of pulsations that are happening. And you are averaging all these changes on fluxes of the white dwarf. But if you look here, you have like a very large peak where you can build just one spectrum, which is the red one that I'm showing here. And that red corresponds to just one very heat spot that is on the surface. So then I'm going to fit the spectrum to measure the abundances just in this area. And then I'm going to compare with the measurements that I got from the blue spectrum. So this is what I got. So I'm just showing for silicon and carbon whether there are more abundances in this system. There is a lot of molecular hydrogen G29-38 that contaminates the other lines, and also interstellar absorption. So these are the two better elements that I could measure. I'm sorry for the people that are at the back that they cannot see like the main results. So carbon it's okay, it's the same, but silicon, there is a difference, but it's still within the uncertainties. They agree. So the conclusions, then, well, I don't think it can be too conclusive whether it's saying that it's homogeneous, the metal distribution. The signal to noise of the spectrum that I was fitting is not great, and also because we just fit one brightening, one peak, and therefore, as an observer, I need more data. But also what I can contribute to the literature is that we can use the surface gravity about 8. Whether here I'm giving the minimum temperature, because the pulsation that will move a bit the point somewhere will do something like this. Yeah, I'm finishing before then. Thank you.
Thank you. Okay. So the next, the next speaker is Matthew Coleman. And he's going to talk to us about convection affects magnetic turbulence in white dwarf accretion disks.
Yes, thank you. So first off, that's a little bit of a mouthful, so I'm going to change it slightly to understanding outbursts in white dwarf accretion disks. My name is Matt. I'm a postdoc at the IAS. I'd just like to really briefly thank all my collaborators. There's a bunch of them. So first off, I need to get everybody on the same page about accretion disks. This is largely an accretion disk work, but it's about white dwarf accretion disks. So I'm going to start you off here. Now, the first thing to know about accretion disks is they grow on you. Back in the early 70s, Shakur and Shania found this clever way of putting almost all of our ignorance into a single parameter, alpha. Not the mixing length alpha. This is the secure Shania alpha. It's a way to parameterize viscosity in accretion disk or turbulence. So just think higher alpha means more viscous or more turbulence in the accretion disks. And this parameter has actually allowed us to gain further understanding of these disks. It was really hard to make traction before that. And what sets alpha in ionized accretion disk is the magnetorotational instability. In a linear regime, you can just think of these as two fluid parcels with a magnetic field. It's the same as two balls attached to a spring in a linear analysis. And if you really follow that through, you can see how there's a linear instability there. But I don't have time to go into details about that. So there's two great systems, two great classes of systems for studying accretion disks. So there's these dwarf novae that we've heard about before. So white dwarf accreting from a main sequence companion. And here is a small segment of the light curve from SS Cygni. You have outburst amplitude of about 4, recurrence times of about a month, outburst duration about a weekish, which is within the ballpark of most dwarf novae. And this change in luminosity is just from the accretion disk itself. So this accretion disk, by changing state, is actually telling us about the stress that it has. It's a way of directly probing the turbulence in accretion disks. Without this time variability, we wouldn't have this sort of probe. So that's why dwarf novae are really great systems for this. And so we can go in and try and simulate and understand this. And one quick thing I want to point out here is the outburst duration is a lot shorter than quiescence. This is telling us that the viscous time scale here is shorter. There's more viscosity in outbursts than the quiescence. You can get that just from these observations without too much modeling. But the question is, why is the turbulence difference in these two states? So here's a slightly longer light curve of the same system. Over a century of data here, each row is a little over a decade. Again, this is SS Cygni with amateur astronomy up here. So also, I'm studying a similar type of systems called amcanvans. There's a subset of amcanvans that have behaviors that are similar to dwarf novae. There's outbursts in the accretion disk. I'm focusing on just this subset of amcanvans that I'm going to air quote helium dwarf novae because the accretion is helium, but they exhibit some similar phenomenology. But this type of system also lets us compare how composition affects accretion disk physics. We have these two systems with similar phenomenology, but completely different composition. So we can explain the outbursts in these systems by looking at the thermal stability of the accretion disk. I'm looking at a single radius in the accretion disk, and I'm asking where is this thermally stable in this parameter space of effective temperature and surface mass density. The solid line here is the thermal equilibrium. To the right, heating exceeds cooling, and over here, cooling exceeds heating. The two dashed lines are what happens if you set alpha constant. But from outbursts, we know that you can't have a constant alpha. You have to use two different alphas. And the two choices of alpha here are just done to fit the data. So to explain this instability, the accretion rate from the secondary is driving you to this middle branch, which is thermally unstable. It's an equilibrium, but it's an unstable equilibrium. And if we start down here, we're getting more mass from the donor than we're accreting on the primary. We go up in mass and temperature until we get up here. A little more mass puts us in this runaway heating phase, go up to the hot branch. We're now in outburst and much more luminous. Now we're putting more mass onto the primary than we're getting from the secondary. We go down. A little more mass loss puts us into this cooling phase. Runaway cooling, we restart the limit cycle, and we're in the dim phase here. So that's roughly how dwarf novae outbursts work. But the key here is to now understand why there's two alphas. So if you do a bunch of complicated simulations, and I'm not going to go into the details of all the physics here, you start to learn that there's something interesting going on. So first off, I'm going to really briefly look at the equation of state stuff. Accretion disk people never really thought to look at a non-trivial equation of state, but it's really important for this problem. So the adiabatic index for the hydrogen case, the dwarf nova case, changes dramatically, and same for helium, and this ends up affecting the convection that we see in these simulations. Similarly, opacity also makes a difference in these, surprisingly or unsurprisingly. So I'm looking at the dwarf nova case and the amcanvan helium case. Each color here is a different simulation. The gray lines are the opacity curve at a fixed density. Ignore this orange simulation for now. So this blue line is the evolution of a single simulation. It oscillates up and down throughout its the simulation duration. And when it's up here at hot temperatures, high opacity, it's convective. And when it goes down here, it's no longer convective. So we see intermittent convection in this simulation. Similarly for the green simulation over in the Amcan-Van case. But this blue simulation here, it stays between the two ionization peaks of helium, and it actually persistently stays convective for the duration of the simulation. So that's an interesting difference that we see just due to composition in these two systems. Okay, when you put all these simulations together and each point on this plot is a different simulation, we can make an S-curve just from the simulations. So this is the same S-curve I showed before, but now with simulation data. You'll see that there's no middle branch because simulations don't stay in an unstable equilibrium. The color I have here corresponds to this alpha viscosity parameter, and we're seeing a nice high viscosity. This time it's only at the tip of the upper branch instead of the whole upper branch, which was parameterized before. But we're getting nice good agreement with the earlier predictions of a high alpha in an outburst. So we've got more turbulence in outbursts. We're doing the same thing with the Amcan-Van case, and this is just a zoom in of this area here. Colors, again, are alpha with a high alpha at the tip of the upper branch. Okay, so the question then becomes, why is alpha higher in outbursts? I'm just going to focus on the right panel here. Each symbol on the scatter plot is a different simulation. The color of the symbol tells you the angular frequency of that simulation, so which radius that simulation is done at, as well as the composition. So purple's the only Amcan-Van simulations. The symbol shape just tells you which part of the S-curve it's on. And here, so this is alpha times the square root of the mean molecular weight. And so you see great correlation here. And this x-axis is essentially the speed of convective eddies normalized to the sound speed. And so the faster the convective eddies that we get in our simulations, the higher alpha is, the higher the turbulence is. And what turns out is that the convection is actually interacting with a form of magnetic turbulence, the magnetorotational instability. And so convection is boosting the MRI, but it's still the MRI that's dominating the stress and turbulence in the accretion disk. And if we put everything that we learned about our 3D simulations into a 1D light D curve, we get these for a dwarf nova outbursts. There's some funny business with this weird zigzagging decay from outbursts that we believe are numerical effects from trying to put a 3D simulation into a 1D code. There are some simplifications you have to do in order to make that work. But we get roughly the right amplitude and roughly the right recurrence time. So we think we're doing a pretty good job here, and that this is a nice piece of evidence kind of closing up the loop on what causes dwarf novae to actually work. And so now that there's good clear grounds to say that it's convection that enhances the MRI and outbursts and actually makes dwarf novae work the way we see them. Okay. So, dwarf novae and Amcan-Van are great systems. Their time variability lets us probe accretion disks. And we find that convection actually enhances the viscosity in these accretion disks by about an order of magnitude. And this raise in alpha is highly correlated with convection. And so this now puts the theory on great, stronger grounds and puts this enhancement of alpha on with a now good understanding. So, thank you.
We're gonna have one more talk for questions. The lady.
Thank you. Okay. Yes. Which one's the laser? The laser is the green. Yeah. Cool. Excuse me. Sorry. No problem.
So the next speaker is Claudia Velarde. She's going to talk about a search for disintegrating asteroids and substellar companions in photometric systems.
All right, can everybody hear me? Cool. Hi, I'm Claudia. I'm from the University of Leicester. I'm a PhD student. And as Fabiola said, I'm going to be talking about the focus on my thesis, which is searching for planets around white dwarfs in different surveys. So just to give you a little bit of an outline, my project is divided into two main chunks, and so will my talk. I have been looking at some ground-based data that I collected from South Africa, and then I also have been looking at some space missions, Kepler-2 in particular. So for the first part of my talk, I'm going to be talking about this survey of metal-rich white dwarfs that I've been undertaking. The reason why I chose DAZ is because of the discovery of WD 1145 plus 017, which is a metal-rich white dwarf that also has a circumstellar disk. And in 2015, it was found to have orbiting planetesimal, disrupting planetesimal in front of it. That were actually eclipsing the star with a period of 4.5 hours. For that reason, I went to SAO in southern South Africa, and I used the 1-meter telescope with shock, which is a high-speed camera that is ideal to observe white dwarfs because of its very low readout speed, which enables us to take data with very short cadences. And for those of you who don't know, eclipses around white dwarfs, if it's planetary object, they don't last very long. They only last about a couple of minutes, so short cadences is crucial. So far, I have looked at 52 objects, mainly DAZ, both with and without disks, and then a few hot white dwarfs that are known to have metal pollution. The reason why I decided to observe DAZ that also had no disks, even though WD 1145 has a disk, is because of two main reasons. The first one being that they still may have disks, just too thin for us to see in the spectrum. And the second one is due to an orientation, I would say problem, but not really a problem. It's just that whenever we want to spot disks around white dwarfs, we need the disk to be as face on as possible. While if we want to see eclipses, we want the object to be as edge on as possible. So if we're looking for planets, these stars, they might still have disks. It's just that we don't see them because the planet that's eclipsing the star is edge on. Sorry, I forgot to say. Because of the period of WD 1145 being 4.5 hours, I wanted to simulate that as much as possible. So I've been looking to at different objects with periods between 2 and 7 hours. The shorter end of the periods being due to observational constraints, so whether the object was more or less visible during the night. I use cadences of 5 to 60 seconds, depending on the brightness of the objects. So, big shocker, we did not find any planets. However, I did find a new variable object. This one is a metal-rich white dwarf with a known gas and dust disk. However, previously no photometric variability had been found on this object, although we found this very nice 1% variation in its light curve with a period of about 2.5 hours. We are currently awaiting for spectroscopic follow-up in order to see if there are any signs of variability in the metal lines and in the radial velocity of the object, looking for any possible hidden companion. So in terms of stats, I realize this is very, very small number statistics, but just to give you an insight, if I just took my whole sample and put WD 1145 in it, this would make the fact that we didn't find, this will make the chance of finding planetary systems around white dwarfs down to less than 2%. So these are very rare systems. From other literature, we know that this is even like a very high number. It's actually a lot rarer than that. However, as I said, this is very small number statistics. And I am very confident that we did not miss any transit-like event because 1145 has transits that go between 10 and 50%. and our noise level it allows us to detect anything within a few percent. So what's going on? Why do we not find anything? There are a few reasons. First of all, being that there simply isn't anything to find. However, that's very unlikely, especially with the discovery of WD-1145. And now I think there are a few other objects that are not eclipsing, but there is evidence for other planetesimals. It might just be a problem of just looking at things that are on the wrong inclination. So white dwarfs are very tiny objects. For something to eclipse them, there is a very, very narrow range of inclinations that we can look at. The length of the observing window is another big problem. As I said, we can only observe objects for a few hours at a time, and so we might have just missed the event, or we were just not looking for long enough. Some smaller objects like tiny asteroids, rubble piles, dust trails may just be simply too small to be detected within our noise level. And also, my sample is still pretty small, and so we might just not have seen that because we haven't looked at enough objects yet. To address this last problem, I'm actually looking at more objects. I'm continuing my survey at SAO. I have about 8 more weeks scheduled so far. I will be looking at white dwarfs that are in the Next Generation Transit Survey, and with tests up and running, I will be looking at that too. Speaking of space missions, this brings us to the second part of my talk, and I have been looking at data from the Kepler-2 mission. However, in this case, I just looked at any white dwarf, any non-binary white dwarf, not just metal-rich ones. So the Kepler-2 mission is a space mission that looks at fields that are only on the ecliptic, and it observes every field for about 75 days. Although in the original Kepler mission, where WD-1145 was, there was only 20 white dwarfs, we expect by the end of K2 to observe 20 to 2,500 non-binary white dwarfs. So that's a lot larger sample. The main limitation of Kepler-2 is the cadence. So the cadence is almost half an hour. So that kind of limits us to look for periodicities that are at least an hour long. There is some short cadence data, but not for all objects, so it's not ideal. And also there's a very quite annoying feature in the K2 light curves, which is this sawtooth feature that is due to the fact that in the early stages of the mission, one of the stabilizer wheels failed, and so now the telescope drifts down and then has to be repositioned every 0.245 days. So despite all that, we did find a very new, exciting eclipsing system of a white dwarf with a brown dwarf. Here is the light curve. And here, we can see the primary eclipse. However, we can't say how deep it is due to the fact that the depth of the eclipse is mid over the 29.4 minutes. So Steve Parsons took some follow-up data using UltraCam. And here you can see the U, G, and R filters respectively. And we have a very beautiful 100% eclipse, primary eclipse. And also, we do not see any signs of secondary eclipses or reflection effects. However, this is not that surprising because the white dwarf in question is quite cool. It's just short of 10,000 degrees. And with a period of 133 minutes, we do not expect the brown dwarf to be irradiated enough to produce a big reflection effect. Actually, prior to the discovery, we already had gotten some Force2 data on the object. However, this was part of a bad weather program. So as you can see, the spectrum trail is not that great. I apologize for that. However, here I'm representing the H-beta trail, H-beta line trail. And this is just the 0 point. And it's just to show you that there is quite a clear change in radial velocity. However, from these spectrum trails, we cannot see any sign of metal contaminations. They're just not great. So yes, just to conclude, we've discovered a new eclipsing brown dwarf white dwarf system, which are extremely rare. There is only 3 more known so far. And we are in the process of fitting the light curves that we've obtained, and we are waiting for additional spectroscopic data in order to better constrain the properties of the system, such as the radii of the 2 objects, to obtain a model-independent mass for both companions, well, for the brown white dwarf and the companion, and the orbital period of the system. Kepler-2 is slowly dying. It's almost at the end of its lifetime. I believe right now it's paused as well. But there are still a few campaigns, hopefully, to come out. And there are definitely a few campaigns that I still need to analyze. So we'll see what comes out of that. Thank you very much.
Right here, questions?
I have a question for Claudia.
Yeah.
I don't want to say the exact number, but I remember the number to find transits around normal stars would be of the order of 40,000 stars that you need to assemble. So
Oh, yeah.
Have you calculated what is the probability?
No, that's what I said. That's just a very upper limit, just considering the sample that I've been observing. The actual probability is I think it's 1 in 1,000.
Super lucky to find something.
I mean, I haven't looked at enough objects yet, but it's of the order of 1 in 1,000. So, yeah.
Another question.
Yeah, Claudia, it's a great
Yeah,
work.
thanks.
With your ground-based observations, you had one variable target there.
Mm-hmm.
Was that light curve the only light curve?
No, I do. That's just a snippet from the first time that we observed it. I've got some follow-up.
Okay.
Yeah.
Found the same period as
So far, we'll see what it comes out of it.
Questions?
A question for Matthew. Do we understand the disk in the low state well enough to say, can you have a sort of permanent low state? In some of the AMC games have never outbursted at 9.
Yeah, so there's at least one Anchorman that I'm aware of, I think more, that is in the permanent low state, or as far as we can tell is in the permanent low state.
Do your models allow that?
Yes, my models do allow that. Yeah, they do.
So Matthew, your outbursts had sort of an asymmetric shape. Have you been able to reproduce the ones that are symmetrical and the ones that are up to, 7 or 8 magnitudes, amplitudes?
So definitely not the high amplitude ones for sure. Nothing that high. As for symmetry versus asymmetric outbursts, there are a lot of minor issues with how we basically shove the square peg of 3D simulation data into this round hole of 1D light curve modeling, and that gives us a lot of challenges in getting the shape right at all. That's why we see these interesting decays from outbursts. And there's no clear path to resolving that with that method. I think you just have to try something that's more complicated than a 1D light curve model.
What is the effect of geometrical cancellation when you integrate over the surface of the star?
When I do the integration to calculate the white dwarf model. You repeat the question? What is
The size of the spot is smaller.
it covers about 30% of the white dwarf surface. Yeah, just using one white dwarf model can reproduce the spectrum for just that hotspot because the other one is quite diluted by it's blocked by the emission from this spot. Any more questions? So let's thank our speakers again. Thank you. Okay, we'll put the next speaker. So our next speaker is Eric Dennehy.
That's great.
He is going to talk to us about dusty exoplanetary debris disks in the single temperature black body plane.
Okay, thanks Claudia, thanks Fabiola for that introduction. So I'd like to start off my talk today by examining two very different perspectives on the dusty exoplanetary debris disks and the circumstellar environments we'll be exploring today. On the left, we have the artist's impression of what this system might look like. It's a nice visual, and I always appreciate the work that comes out of these efforts. But on the right, we have the same interpretation by a group of theorists that just recently came out of Cambridge. And while I enjoy the plot on the left, I could look at the figure on the right all day long, because they somehow, in one figure, managed to capture all of the physics that we can probe in these systems on one plot at the relevant, appropriate scales for everything. It's beautiful. This plot just came out maybe a few months ago, and I wanted to call some attention to it for those that are interested in the field and may have missed it. And so Odette gave a nice introduction to these systems. And so just to review quickly, what we're talking about are debris disks of disrupted planetary remnants, which have been scattered in, fall within the Roche lobe limit. They're disrupted. They settle into a nice dusty configuration. The inner edge of that disk could be terminated by a sublimation radius where we have gas production. And now all of a sudden you can have an interacting dust and gaseous phase within the same circumstellar environment, which can lead to viscous spreading outward or viscous accretion inward onto the white dwarf surface at very different scale heights, but as far as we understand it, appropriately the same radii. So there's a third perspective that I'd like to talk about today, and that's that of the observer. So from an observer's perspective, if we're interested in studying these disks, there are usually two avenues with which you can do that. There's the near-infrared excess flux, often reproduced from the light that is absorbed and re-radiated by the dust disk. And occasionally, very rarely, we also see a contribution from the gaseous disk in the form of double-peaked emission lines, typically at this calcium triplet at 850 nanometers. Now, there are also instances in which we've observed gaseous debris in absorption. Those won't be the focus of my talk today, but they also are another nice way to observe both the dusty and gaseous debris disks. So having both the dusty and gaseous debris visible is a fantastic way to provide independent constraints, geometric constraints on the circumstellar environment that you're interested in. And unfortunately, though, we don't always get both when we find a new dusty debris disk hosting system. In fact, for every dusty debris disk system hosting system which we've observed with the near-infrared excess, only 1 out of 5 tend to show gaseous debris in emission, and only less than 10 such systems are currently known. And so while they do provide a fantastic set of independent constraints for us to probe this very rich field of accretion disk physics, we don't really have a large sample to work with right now, and that's sort of the focus of my talk. Fortunately, we were just introduced to a massive sample of new white dwarf systems, and a quick cross-correlation with Guy-NY's could provide hundreds of new dusty debris disk candidates that come essentially free. All this photometry is publicly available from all sky near-infrared surveys, but recall only 1 out of 5 of them should be expected to host gaseous debris in emission or less. And it's not, while the photometry is free, the follow-up spectroscopy is not. And those of you that have ever taken a white dwarf spectrum, you typically don't center your spectrum around 800 nanometers. There are not a lot of interesting white dwarf absorption features out there. And so you really have to target these. And we're hoping to develop a new way, or what I'll talk about today is developing a new way to target these using sort of an informed target selection from the near-infrared photometry. So that becomes the central question of this talk. Can we use any of the inferred properties from the dust to inform our selection for targets of new systems which might also host gaseous debris in emission. Another way to think about that is, are there any systematic differences from the near-infrared contribution from the dust alone between the systems which do host gaseous debris in emission and the systems which do not? And so typically, if you're modeling the dusty contribution of a dust or of a disk around a white dwarf, there's a very common model that gets applied today. It's a 3-parameter model that assumes a flat, optically thick configuration, and your free parameters are an inner temperature, an outer temperature, and an inclination. It does a very good job reproducing the data that we've observed, and it's applied almost universally now to any new dust disk discoveries. Unfortunately, there's a strong degeneracy between the outer temperature and inclination, and this is really exacerbated by the fact that we often only have 2 to 3 points of significant infrared excess with which to fit these models. So we're fitting 3 points to 3 free parameters, not an ideal situation. And so what we tried was to take it a step down, go for a simpler model, one which does not adequately describe what we think we're physically looking at, but does do a decent job of reproducing the data in the bands that we observe, and that's that of a single temperature black body. So our dust disks are neither at a single temperature, nor are they a spherical object. And so again, this is not a very physically motivated concept, but it does do a decent job of reproducing the data in the bands that we observe. And so with that in mind, we started with a sample from a paper in 2015 by Marco Rocchetto, a sample of 35 dusty infrared excesses that were verified with Spitzer space-based photometry. So it's a relatively clean sample, free of contaminants. And this is our first look at the single temperature, what we've dubbed the single temperature black body plane, and where all the dusty debris disks lie in it. So first impressions, there are a few obvious features where there are no dust disks up here, but that makes sense with what we understand. These are higher temperatures, higher black body temperatures, and we expect the dust to sublimate entirely into gas at temperatures somewhere between 1500 and 2000 Kelvin. So that makes sense. Fewer dust disks in this region down here. Of course, this is the direction of decreasing luminosity, and so they're fainter, more difficult to find. So that also makes sense as a selection bias. Most of the disks sort of aggregating central temperatures between 1000 and 1500 Kelvin, exactly what you get when you fit an appropriate dust disk model to these systems. And so now if we add onto this plot the systems which also host gaseous debris and emission, we see that they form this high temperature boundary between the region of systems that do not host dust and systems, or the region where there are no systems or dust systems found whatsoever. And so we could stop here and immediately say, I think that we can say confidently that this is the region, at least in the single temperature black body plane, where we expect to find new dusty debris disk systems which also host gaseous debris and emission. So if you make this plot with a new sample and you're interested in finding new gaseous emission line systems, this is where to look. This is where I would say point your telescopes first. But we have a new tool, a new plot, something to work with, so we might as well speculate. See if we can come up with a physical reason for why we would expect the systems to lie there. And so one way to interpret this plot is that if you are at a given temperature, going up along this axis, so along the radius axis, is sort of increasing in brightness, brightness of the debris disk. And so we could say that maybe something else in these gaseous debris disk hosting systems is artificially brightening the dust. And to give you an example of what I mean by that, I've highlighted two systems which are along this boundary but do not host gaseous debris and emission. I know because I've checked very hard. nothing to be found there. And these systems are white dwarf, it's SDSS, I'll just give you the short names, J1557, which was recently found to be a circumbinary system. So there's actually an extra L dwarf in this system that's contaminating our photometry. So that's why it has made it up here. And GD16, or white dwarf 0408-041, which at the time of its discovery was known to have an unreasonably bright disk, one that required actually a separate model than the one that was applied, a flared disk model, to even describe some of the infrared properties. So we've always known there was something weird about this disk. Another way to interpret this plot is that if you are going, moving along the x dimension for a given surface area or projected surface area, the gaseous debris disks line up as sort of the hottest, or the disks with the highest average temperature, which is effectively what we're fitting with this black body temperature. And that's also a reasonable way to interpret this plot, I think, because we know that at the inner edge of all of these systems, there should be some gas production going on, terminating the dust at the sublimation radius. So they should all have gas production, but unless you're outpacing the viscous accretion from the gas at the inner edge of the surface down onto the white dwarf surface, it will never actually have a chance to build up. So maybe at higher temperatures, you reach high enough gas production rates to sustain a gas disk in these systems. So that's sort of two different dimensions in which you can interpret this plot. And I'm sure that there are plenty more. Those are the first two that came to mind for us. So with that, I'd like to thank everybody for listening, and I'll be happy to take questions at the end of the session.
Thank you, Eric. So we have one more talk for this section. Okay. I can hold it, maybe. No, because you're not good. Okay, there's this. So our next speaker is Yui Xu. Okay. And she's going to talk to us about infrared variability of G2938.
Yes. Okay. Wait. Pointer. Okay. All right. Hi, everyone. I'm sorry I'm standing between you and the launch, but hopefully you will find it worth the wait. So I'm Si Yi. So today I will talk about infrared variability of G29-38. This is actually work done with quite a few people here in the audience. It's a paper we submitted earlier this month. So in the abstract, actually, it was two objects. But for the interest of time, I think I'll just focus on G29-38. If you want to know what is the other object, talk to me or just wait for the paper. Okay, so you might ask why G29-38, right? I think it have many wonders. So let me just list them briefly, and you already hear a few of them yesterday and today. So it's a hydrogen-dominated white dwarf, temperature log G. Even with Gaia, I think it's kind of hot. We somewhat know what's happening, and it's very close, and also it's very bright. It's 13th magnitude, and it really helps a lot. And we also learned, and it's actually sits in the instability stripe. So after talking to Mike, I was told it's not really a favorite for the pulsation community. It's actually a mess. But because it's very bright, so you can observe it for a long period of time and understand what's going on. And then, from my perspective, it's really interesting because it's the first to show infrared access. It also shows 10 micron silicate emission feature, and it's a very heavily polluted white dwarf. So from previous talks, we know that these are planetary debris that went into the white dwarf tidal radius and got disrupted. And the white dwarf is accreting from its circumstellar material. So now we know about over 40 of white dwarfs that show infrared access. And we also know like many more polluted white dwarfs. The new addition for the wonder is I think we discovered the molecular hydrogen in its atmosphere. To me, it's just amazing. It's a 12,000 Kelvin white dwarf, yet you still find a small amount of molecular hydrogen. So in this talk, I will focus on the infrared part. So we already see this earlier. I just want to show it again. So this is a cartoon version of the SED of G29-38. So you see, it pretty much look like a black body in the optical part. And from the infrared, the excess really comes out. So in K-band, about 50% of the flux come from the infrared excess, while in Spitzer IRAC band 1, like 3.6 micron, 80% of the flux from the come from the excess. And then actually in the early discovery in 1987, when they first discovered, you saw the title in an earlier talk, people were not sure where the infrared excess comes from, right? It could, so they speculate it could either be a substellar companion or a dust disk. And then the way out is they thought, oh, so this is a pulsating white dwarf. So the idea would be, what about obtaining a light curve in the infrared and see what happens? So if it also pulsates in the infrared, it means it's probably a disk because it's reprocessing starlight. If there's nothing in the infrared, then it's probably a brown dwarf because basically the heating source is from brown dwarf itself. So this is work done in the early 90s. doesn't look as pretty as all the K2 stuff, but it's sufficient at that stage, I would say. So they got simultaneous photometric observations at different wavelengths. So what you can see is at B and the J band, the dominant period is about 600 seconds. However, at the K band, while the infrared access contribute to 50% of the flux, it also pulsates, but at a different period. And then, so one problem solved is it does pulsate. So this is a strong argument that the infrared access comes from a dust disk. But the puzzle is, why is the period different, right? And then we can look a bit more onto this. This is a cartoon version. This is a white dwarf. This is a dust disk. I'm not a pulsation expert, so I have to put all the modes there so I can get my way around it. So basically the idea is only the mode that would have a net temperature effect on the disk would show up in the disk, while the mode that basically hot, cold, when it cancel out, it wouldn't show any effect. So the 600 period is probably, for example, this kind of mode, right? And then, so basically there's no net temperature effect, while the other like 180, those is probably like this kind of mode. So anyway, so I just think it's a pretty cool idea, and I think we can help out each other here. So by observing in the infrared, we have an independent way to help you identify the mode. And then for us, again, by observing the disk response in the infrared, we can somewhat constrain the disk inclination, because depending on how your disk respond, as Eric mentioned earlier, these disks, it's very hard to characterize, right? It's super tiny and super compact. All right, now I'll move on to our work. We've been extending the observation into the infrared. So this is years of Spitzer, IRAC, and Weiss observation of G29-38. This is at like basically different wavelengths. We didn't really find anything significant, but then there's definitely some low-level variabilities. So here I'm showing kind of the maximum flux difference at different band. It is definitely much larger than the typical instrument stability. I'll get back to that in a bit. So this is in terms of photometry. And then Spitzer also has observed spectroscopically of G29-38 a few times. So here's 3 of the spectrum. So the 2004 and the 2000 spectrum had the exact same setup. And you must think, right? Like the 10 micron feature seems to have changed. So here I'm showing a ratio of the feature. So you see the flux between 5 and 7 microns seem to be more or less the same. But the 10 micron feature has really changed. Could it be due to pulsation, or is this a real effect? Before that, we need to look a bit more carefully about the SED, or the spectrum of G29-38. So again, here is a wavelength, flux. The red are different photometry points, and colored dots are the Spitzer observation. And the green line is the white dwarf model atmosphere. So you see this is a strong infrared access. And traditionally, and Eric have mentioned, we've been fitting these with an like geometrically thin, optically thick dust disk. It works really well. It works for like almost all the dusty white dwarfs. However, because G29-38 is a really bright one, right? And then we have quite good spectroscopy, near-infrared spectroscopic data too. You can see like you really need another component. You need some sort of optically thin dust in order to fit this solid state emission feature. So in this case, we use a very, very simple model. We consider the olivine grains, and we put a very small amount. It's both on top and extend outside to this. And then the black line is our total fit. So you see, it doesn't look great, but it looks decent. So now we have a way to kind of reproduce the whole observed feature of G29-38. Now we can go to assess, okay, what happens to this different component due to pulsation? So the messy part of the pulsation comes in. We were told different modes are not always excited at the same time. So you can't really know, like, unless you have simultaneous observation, you don't really know what the star is doing. So what we can do is we can take the maximum like amplitude and get the maximum temperature difference and try to assess how different components respond to this. So basically here, different lines are showing like how the opaque disk, how the optically thin disk respond to a 2% temperature variation. And then the green line is the total, basically our observed flux. So this is maximum over minimum. So you see, interestingly, the maximum flux difference is at about 3 micron. And then, so I think this more or less explains the low-level variability we have observed at the Spitzer IRAC band. And then for the IRS spectrum, so this is mostly covered around this range, right? So at 10 micron, indeed, there could be about a 10% like maximum flux difference. However, if it's caused by pulsation, we would expect a big flux change between 5 to 7 micron as well. And this is not quite what we see. So again, this is a flux ratio between the two epochs. So from that, we thought probably it's not caused by pulsation just because of the shape of the spectrum really does not look alike. So another idea would be, how about it's the actual change of dust mass? So on the left hand, it's the plot I showed earlier. And on this hand, I'm using the 2007 data. All the other component is the same. The only difference is I put about 20% more dust mass in the optically thin part. So give you a number, it's about 10 to the 17 grams. If you convert to typical asteroid size, it's only 4 kilometers. So it's really a tiny, tiny amount of optically thin dust that can already explain the difference between these two. So what does it really mean? So let's say 10 to the 17 grams over 3 years. Let's just divide up and calculate the accretion rate. Assume it's steady state accretion. And so let's call it dust production rate. So it will be about 10 to the 9 grams per second. And then if you calculate the accretion rate in the atmosphere, like by the heavy metals, it's also about 10 to the 9 grams per second. Though yesterday we heard a few talks, maybe this number need to go up by an order of magnitude, but I think they still more or less agree within order of magnitude. So the number doesn't go completely off, I guess. So I think it seems to argue that continuous disruption of small planetesimals and the production of these optically thin disks can be nearly continuous. Like it's really a very dynamical process. Since we only have 2 epochs of data, it's very hard to see what is really the long-term trend. So observers' famous last word, we need more data, right? So we need more data to figure out exactly what's going on. Future's bright. I guess I'm the only first talk about JWST. So I think all these dusty white dwarfs would be prime target to observe with JWST. And I think photometry is not enough. We really need spectroscopy. As you see, we really need spectroscopy to characterize the whole feature. I know, whenever it launches, right? And then another thing I want to kind of call for attention is, I think we need a full radiative transfer disk model to fully understand different components of the disk. The simple disk, it works, but there's a lot of physics that it really cannot explain. In order to understand the evolution of the disk, we need a self-consistent full radiative transfer disk model. All right, so here's my summary, and hopefully I convince you it's probably not caused by pulsation, and it's probably come from an increase of the optically thin dust. The systems are very dynamically active. Yeah, that would be interesting to study. And then already mentioned about this IAU conference, and hope to see you there. And the very last bit is one little advertisement about Gemini Observatory. I joined the Gemini about a year ago. It's actually a lot of fun, and there are quite a few white dwarf researchers there. I think you know many of them. So the first 3, we are all based at Gemini North in Hawaii. Then the newest employee of Gemini, Eric, the previous speaker, he will be based at Gemini South. And then we have fellowship programs, like 2 positions each year, one in South, one in North. So if you are interested in working with us, please consider applying. So thank you.
Questions, and where's okay? Right there.
Do I need to take it out? Thanks.
So a question for Eric. Have you considered possibly self-heating in the disk? In particular, so I would explain that maybe these accretion rates could be a lot higher. If you get into the regime, it could be kind of 13 grams per second. The viscous heating in the disk could contribute to IR excess. And also, maybe related to that for you or anybody in the community, is there some sort of signature? I think that disk would need to be really massive. From that Ben Sharp paper you pointed out, they got higher accretion rates from viscous spreading only if they had a disk mass almost as much as an Earth mass. So would there be some signature that you could distinguish that kind of a disk with?
Right, so I personally have not considered that, but there has been some literature discussion on those topics. So the gaseous degree disk hosting systems, the ones with gaseous degree emission, tend to have slightly higher accretion rates on average than their non-gaseous degree disk hosting counterparts. So that's sort of part one, I think, to add to the second part of your comment. But another group did recently, and the name is escaping me of who it was, explore infrared variability, short-term infrared variability from changes in the viscous properties of the dust disk. Yeah, I think it was Rafikov. I think it was Roman Rafikov explored that. And so yes, that sort of thing has been explored in a theoretical sense. Applications to what I showed today, I think is a great example of one of the sort of artificial brightening events that could be pushing these things to a higher brightness. And so I would definitely put it in that category.
To see, you modeled these temperature changes in the pulsations as about a 2% temperature effect. Odette's done some really nice work showing fitting cost time tag data both at high and low fluxes to show that they can go all the way up to 4,000 degree temperature changes. It'd be like a 20 or 25% temperature change. And that's going to sweep across that whole disk over a matter of minutes. And so I wonder if you were to model something at 20% level, would you expect really big changes, even integrated over the whole disk?
Right. So I think that's a really good point. But I think there are two aspects to this. One is the Spitzer observation lasts like 10 minutes or longer. So hopefully, ideally, this should be even out. And another thing, it's still the same, is if you take the ratio of the two spectrum, it really seems the change is only centered around 10 micron. Between 5 to 7 micron, there's really not much difference. So even if the white dwarf becomes, I don't know, 10% higher temperature, you would expect the shape to stay. If it's from pulsation, the shape would still be like that. So, yeah.
Just a quick comment to Eric. So you reduce the 3 parameter bit to 2, but I think we can actually reduce it to 1 and just look at the fractional input excess. And then you find that the systems which have gas emission are by and large the ones that are most infrared bright and the largest input excess.
Yes.
I don't know what it means, but it's an even simpler way to.
Right. I'm all for taking the parameters down. Let's go even lower if we can. But so I haven't looked at that, but it would be very simple to do, just because the sample the sample that I pulled from is the fractional infrared excess study. So I don't think I've actually put the gaseous ones on that plot. It would be very interesting to see.
Any more questions? So let's thank our speakers. Just a reminder, please take your posters from the stands and let's have lunch.